Mm.
Definitely that was old model,
Yeah.
but it never gives any problem. All my
Very.
3 years I just completed my PhD and I'm using that.
Okay, good.
So that's the reason I always, I even recently I bought UV visible spectrometer with sir only, Rashekar sir.
Acha, you already purchased or you're planning to purchase?
No, I had UV sir, I purchased.
Acha, from Shimatsu?
Yeah.
Okay. I got confused. So now what are you planning? You're planning a DSC and anything else?
Sir, we are planning DSC, and my colleague actually, when you Vikram, are you there? He's joining. So he told he excited. He works on NMR.
Okay.
So we are developing here central laboratories, sir.
Okay.
So our now under construction.
Planning any GC or something?
Of course, I wrote a project to CRG DST.
For GC? Okay.
Yeah, and I already completed successfully 2 DST projects in IAC, Indian Institute of Science.
Institute of Science, okay.
Yeah, there we had all the facilities. And we don't have space to keep the equipment. So we utilized money, to buy some chemicals and manpower. And after shifting to Geetham, now we need money to buy the equipment. There we had money and we don't have the space.
Correct.
Now the thing is reversed here. So that's the thing. Due to lockdown, it is a final stage actually, my CRG project. So if they have, they might invite to present the project to Delhi or maybe virtually very soon. That's what I heard. If it goes through, maybe I will get some 80 lakhs. That is 80 lakhs project. So definitely, actually in that project, we proposed atomic absorption spectroscopy from Shimadju. Sir has given, Rashekar sir has given budgetary quotes for that.
Okay.
So if I get that project, definitely we will get one atomic absorption spectroscopy.
Achha, atomic absorption also. Yes, good. Very good equipment.
Morning, Mr. Girujan.
Good morning, sir.
How are you today?
I am good.
Wonderful.
Sir, 10 now. Can we start or you want to wait? Kirchen, sir?
I think we can say so. There are already 62 participants, I suppose.
Should we wait another 5 to 10 minutes?
Maximum 5 minutes, not even 10 minutes. Maximum 5 minutes.
So just now received emails from principal sir and dean sir. They will be joining us exactly at 12:20.
Sorry?
They will be joining us exactly at 12:20.
Okay. Good.
How's your day been so far, Mr. Girijan?
Yeah, it was good, sir.
Good. I'm glad to hear that. I'm sorry? What did he say? Did he confirm his presence today?
Hello?
Yeah. He what? Okay, so did he confirm? Right, right. Okay. Mm-hmm. So is he going to join us at 12:30 or something? Is he going to be joining us? Will he be joining us? Good. I did. Yeah. This morning I did. 12:30. Hmm? No, I've already had a conversation. Yo, listen, I already had a conversation with him this morning, and I told him at 12:30 it would be great if we can come over at 12:30 or something today. And he said he actually forgot about it, and he said he will be coming over. He did forget about it. But I reminded him, yo. Hopefully. I'm gonna message him right now. I'll message him. He checks messages.
I think we should start now, sir. It's already time up.
Sure. Yeah.
Shall we start, sir?
Yeah, we should. We should.
Good morning, everyone present here. I, Dr. Srilakshmi, convener of the National A Workshop on Modern Analytical Techniques for Material Characterization. So we have successfully completed 3 days, and it's my pleasure to welcome you all to the fourth and the last day of the workshop on behalf of Gautam Deemed to be University, Bangalore and Chemistry Department in association with Toshwin Analytical Private Limited. Today's session is on gas chromatography. Gas chromatography is a common type of chromatography used in analytical chemistry for separating and analyzing compounds that can be vaporized without decomposition. Typical uses of GC include testing the purity of the sample or separating the different components of a mixture and their quantification. GC may help in identifying a compound. Choosing a right column, type of detector, and method development is very important for the proper separation and identification of compounds. It would be nice if Girjan sir could cover these topics in this session, which would be very helpful to the researchers. I trust today's session is also as fruitful and successful as previous sessions. So welcome to you, sir. Girjan sir, screen is yours.
Yeah. Thank you, Dr. Lakshmi. And very, very warm welcome to all the participants. And today we are on the fourth day of the series, the last day of our webinar series. And I hope you enjoyed the last 3 days discussing 3 different topics. And today we have a very, very interesting topic to discuss, gas chromatography. It's a wonderful separation technique. So before I go to today's topic, as usual, I'll be taking some 2 to 3 minutes time to ask you the questions I gave you yesterday. I will read out the questions. Number 1, to all the students, the questions are all for the students. What is the type of information available from a thermal analysis system?
Nothing. I didn't do anything.
What type of information
I didn't
can
do
be
anything,
available from a thermal analysis system? Any question coming in?
Earphones పెట్టుకున్నాం. Earphones ఉన్నాయి.
So what is the type of information that is available from thermal analysis? That was my first question. Any answer coming in? Phase temperature, thermal stability of the material, composition. In a very simple sentence, we can say we can find out what are the chemical and physical changes that are taking place in the sample when it is subjected to either heating or cooling under a controlled condition in a specified atmosphere. So that can be the right answer. And the second question, technique for dimensional changes. What type of a technique you will use for understanding the dimensional changes? TMA, right answer. It is a thermomechanical analyzer that can be used for dimensional changes. So wonderful. What is the additional information you can get from DSE as compared to DTA? What additional information you can get from a DSE experiment? It is not exactly purity. There is something else. What additional information you can get from DSE as compared to DTA? So the right answer will be you can get the
right answer came in enthalpy.
Enthalpy, yeah, correct.
Yeah, 2 people.
Prachi Desai
and Kalavani.
Okay, very good. So the enthalpy, change in enthalpy, that is what we measure, dH by dt. The change in enthalpy is available from a DSE experiment as compared to DT. What is the reference material that we normally use in a DSE experiment? You can name alumina. Correct answer, alumina. Al2O3 is a very commonly used standard reference material for DSE analysis. And the last question is a very, very simple question. Suppose if you want to find out the moisture content in a sample, which TA equipment you will use? Thermogrammetry, correct answer. We will use a TG for that. by using a thermogravimetric equipment, we can find out the moisture content in a sample. So I think today the response was quite good. I'm so happy. And with this, I think we'll go to our topic of discussion today, because I have got a time cap. I need to stop my presentation by 12:15, and today, because of that, today we are not having a discussion on the software also. So I'll start sharing my screen.
Sir, Ramesh Gonduri asking one question. Maybe we will take this question at last.
We can take it up. Please. We can. There is a session now. We can take it up.
Okay.
So the slide is visible, everyone?
Yeah, yes.
Okay. So let us start with the last day's topic. We are going to have a discussion on gas chromatography, a very, very powerful separation technique. Okay, we are all used to chromatography. I know all the students know what is chromatography all about. When you talk about chromatography, it is a technique which is more than 120 years old. The birth of chromatography was in the year 1905, when a Russian botanist, T. Sweat, tried to separate some plant pigments on the basis of column chromatography. You can imagine 1905, almost 115, more than that. There was no instrumentation available. There was no column technology available. No sample introduction technology available. No detection mechanism, nothing. It was a very crude way of separation. What it did is took a very long glass column, very long and wide glass column, and filled it up with calcium carbonate. Calcium carbonate is an adsorbent material. And then he had a solution which he took out from a plant material, which is containing different material, different compounds. He wanted to separate it, and he poured the solution from the top. There was no pumping system available. The solution what he was pouring from the top has to come down the tube purely by way of gravitational force. And then to take it down, he had to use a lot of solvents. He had to pour a lot of solvents to take it down the tube. And it's a very, very slow process because the whole thing was traveling purely by way of gravitational force. Now, during the course of this experiment, he had a very, very interesting observation. He found different colored rings forming at regular intervals. And these colored rings were moving at different speeds also. But probably at that time, he was not able to give a reason for that. He was not able to explain why this was happening. And that was it. That was an observation which he recorded. And nobody gave much attention to this. So for another 50 years, this was a totally neglected technique. It was totally neglected technique. Then the actual breakthrough in chromatography came in the year 1953 when James and Martin shared Nobel Prize for the separation of fatty acid methyl esters by the gas chromatography. We can consider that was the beginning of modern days chromatography. Now more than 50, 60 years have passed. A lot of developments have taken place. Developments in terms of column technology, developments in terms of sample introduction technology, developments in terms of different types of detectors, then development of a very powerful software. A lot of things have taken place, and today we have a very, very powerful benchtop model of a gas chromatograph or a liquid chromatograph, which is capable enough to separate even the most difficult naturally occurring compound. That's the power of chromatography today. And chromatography has become a, I mean, we have come to a stage where nothing can be, we cannot do away with chromatography. In every sphere of life, there is an application for chromatography. So it is a wonderful technique for different types of separations. So when we talk about chromatography, it is all about separation. And we are all used to separation. There are a lot of classical methods of separation available. So right from a simple filtration, when you are making a cup of tea at home, we are basically boiling tea leaf with water, and finally we are going to filter it. And by doing this filtration, we are separating the solid particles from the liquid. It's a separation mechanism. When you are going for distillation, we are going to separate two different solvents or two different liquids based on the difference in boiling. But it's another way of separation. But all these are like distillation or filtration or centrifugation. All these are classical methods of separation. Now, when we talk about chromatography is also going to do the same thing, separation, but it is going to do it in an automated way. That's only difference. Okay. So let us come to some of the basic things understand some of the basic things about chromatography. Here I have written a powerful separation technique. When we talk about chromatography, especially gas chromatography, gas chromatography can be applied only to volatile samples. So that is, when you talk about any analytical technique, whether it is chromatography, whether it is spectroscopy, any analytical technique has got certain limitations and certain plus points also. So similarly, when it comes to gas chromatography, it has got two limitations. One is it is applicable only for volatile samples. So that means your sample has to be volatile. Second condition is your sample has to be thermally stable also. That means most of the time, in the case of gas chromatography, we are going to heat the sample and we are going to convert the sample into vapor form, gaseous form. So there are certain samples which will undergo decomposition or degradation when it is heated. And those type of samples are called thermolabile samples. And they also cannot be directly analyzed by gas chromatography because the moment you start heating, the sample will undergo decomposition. So the conditions, the limitations are the sample has to be volatile and the sample has to be thermally stable. That means when I'm heating the sample, it should get converted into vapor form without any sort of degradation or decomposition. So these are the two limitations for GC you have to always keep in mind. Before you analyze a sample, you have to see what is the volatility of the sample, and you also you should know what is the thermal stability of the sample. Chromatographic technique in general, it is a physical separation method. Why we say physical separation method? There is no chemical reactions involved in chromatography. Only physical interactions are present. That's why we say it's a physical separation method. And for any type of chromatography to take place, the minimum requirement is you should have two different phases. One is a stationary phase, one is a mobile phase. These two phases are required in any type of chromatography. Whether you talk about GC, whether you talk about HPLC, we talk about IC, we talk about SFC, we should have two different phases, stationary phase and mobile phase. And when it comes to GC, your stationary phase either can be a solid material or it can be a liquid. And into bracket, I put approximately, it's a very approximation, 10% against solid weightage and 90% weightage is given to liquid. What does this mean? So that means I can use a solid stationary phase for approximately 10% of the total gas chromatographic applications. In other way, I can say if I get 100 samples for GC analysis, maybe around 10 samples can be analyzed using a solid stationary phase. Remaining 90 samples I can analyze using a liquid stationary phase. That's why a very rough approximation weightage is given 90% liquid, so 90% weightage for liquid and 10% weightage for solid. So when to be a little more specific, solid stationary phases are used for gas analysis. Most of the time, when you have a gas analysis, different types of hydrocarbon separations, refinery gas separations, noble gas separations, or natural gas separations, then you go for a solid stationary phase. So many people who are involved in gas analysis, they prefer a solid stationary phase. And the rest of the compounds, we prefer, for example, pharmaceutical analysis, environmental analysis, perfumery analysis, food chemistry analysis, we prefer a liquid stationary phase. So liquid stationary phase is more versatile, more widely used. That is why that different weightages are given. And mobile phase is always a gas, an inert gas, and that is why it is called a gas chromatography technique. And why we are going to use GC? What are some of the advantages? Short analysis time. If you compare HPLC analysis and GC analysis time, normally you find GC has got a shorter analysis time compared to LC. And we have got plenty of stationary phases available. But in the case of LC, you may not find that many number of stationary phase. When I tell stationary phase, I am going to refer to column now onwards. At the moment I say column, I am referring to the stationary, because the stationary phase is always present inside the column. So if somebody is talking about the column, he is referring to stationary phase. Okay. So we have got plenty of columns, plenty of stationary phase available for GC. Similarly, we have got different detectors for different types of applications. And it is a comparatively simple method. Ease of operation is there. It's not a very complex system. And so these are some of the inherent advantages of using a GC. What is the goal of carrying out a GC analysis? The first sentence I'll read: to separate mixtures of organic compounds. Now, naturally, for students to understand, you may ask me why you cannot use it for inorganic compounds. But then you think about what I told you before, the limitation of GC. GC is useful only for volatile samples. Most of the inorganic compounds, you talk about an oxide, you talk about a salt, you talk about an inorganic chelate compound, most of the inorganic compounds are non-volatile. They have got a, under the conditions of GC, because GC has got a certain maximum operating condition, operating temperature. So when you look at that operating temperature, maximum possible temperature for GC, all these inorganic compounds have got a temperature. They are totally non-volatile. They will lie outside the temperature of GC. So we cannot analyze those inorganic compounds because they are totally non-volatile from the GC point of view. At the same time, we can analyze certain inorganic compounds which are already in the gaseous form. Means what I mean to say, you can use it for some gas analysis. Suppose atmospheric air, you know what is the composition? The composition is 79% nitrogen and 21% oxygen. I can separate nitrogen and oxygen atmospheric air by GC at room temperature, even without heating. Room temperature I can separate with a 1 meter molecular C5A column and a TCD detector. I can separate nitrogen and oxygen in atmospheric air. It's an inorganic separation. It's a gas analysis. Carbon monoxide, carbon dioxide separates a very extremely critical application in some of the fertilizer companies and petroleum companies. And we can separate it by GC, carbon monoxide and carbon dioxide. It's an inorganic analysis. We can separate oxides of nitrogen, oxides of sulfur. But all these compounds are already in the gaseous form. So for us, there is no problem. So GC can be used for a very limited number of inorganic compounds which are already in the gaseous form. Barring these compounds, the rest of the inorganic compounds are out of bound for GC because they are totally non-volatile. At the same time, most of the organic compounds, and there also there is a cap. Most of the organic compounds having a maximum molecular weight up to around 600 only can be analyzed by GC. There are a lot of organic compounds which will be having molecular weight much more than 600. You talk about a peptide system, you talk about a high molecular weight biopolymeric system. They are all having a very high molecular weight, and because of that, they become non-volatile. And they are to be analyzed by HPLC, not by GC. So normally you can say GC is meant for low molecules, small molecules, organic molecules, organic compounds having a maximum molecular weight up to around 600 can be analyzed by GC. And then we can identify and quantify using reference standards. So if you are getting a sample, you can use a GC system, and then you can separate all the compounds. And then you can, for identification and quantification, you require reference standards. If reference standards are not available, you will not be able to identify what are the compounds that are separated by the column, and you will not be able to quantify them. This is equally applicable to HPLC also. What is the block diagram of a GC? Now you have a sample. Suppose you have a sample which contains 2 or 3 different compounds, A, B, and C. You want to separate it. You have to introduce the sample into the GC system. And what are the main parts of the GC? One is there is an injector. Injector is the place where you are going to inject the sample. And once you inject the sample, the injector is kept at a high temperature. You need to optimize the injector temperature depending upon your sample. So when you inject the sample, introduce the sample with the help of a microliter syringe, an extremely small quantity of the sample is all what is required in GC in microliter quantity. Normally our injection volume is like 0.2 microliter, 0.5 microliter, sometimes even 1 microliter. not more than that. Such a small quantity of sample we are going to inject into the injector port, which is heated and kept at a high temperature. This we need to optimize from sample to sample. The injector at this temperature, the moment you inject the sample, it will get converted into vapor. Now what is your mobile phase? Mobile phase is a gas, and that gas is coming from a cylinder. So you should have a proper gas cylinder also. Depending upon what type of a gas you are going to use as the mobile phase, you should have the cylinder with you. And the cylinder is also, the gas from the cylinder is also coming to the injection port. It is also coming to injector. So there is a connection from the cylinder that is coming to the injector port. And you are injecting your sample also there. The sample will vaporize because of the temperature. So the sample vapor will mix with your mobile phase, that is your carrier gas. And they both together, they will go to the column. Column is nothing but the stationary phase. And the actual separation takes place in the column, inside the column. And how the separation is taking place, that is what we are going to see in one of the slides now. And different compounds will be coming out of the column at different times. And the moment the compound comes out of the column, it is entering a detector. Now, column is also heated separately, independently heated. Your injector is independently heated, your column is independently heated, and your detector is also independently heated. And the moment the compound comes out of the column, it will come to the detector, and the detector is going to give an electrical signal. And that signal intensity is directly proportional to the concentration of the sample. That is how we can quantify it. And that signal will be processed by your software, data processor. And then you can either go for a qualitative analysis or a quantitative analysis, provided you have the required number of reference standards with you. If that is not available, you will not be able to identify the compound and you will not be able to quantify the compound. It's as simple as that. So this is what exactly I told you. This is what is written. A flow controller is the injection port, column, oven, detector, data. We'll see this diagram. This diagram is more informative. So I'm showing a carrier gas. Carrier gas is nothing but your mobile phase. It's a gas. I told you it's an inert gas. So there is a cylinder. And the cylinder, you can see the cylinder is connected to, there is a connection coming from the cylinder, and the gas is flowing from the cylinder and it is coming to the injection port. Okay. And before coming to the injection port, there is something what is shown as a gas flow controller. Your gas flow controller is required to regulate the pressure that is coming from the cylinder. Because when you purchase a new cylinder, it's at a very high pressure, approximately 140 to 160 kilograms per square centimeter. It's a huge amount of pressure is there in inside the cylinder. But what pressure we require on our GC system is hardly 6 to 7 kilograms per square centimeter. We need a very small pressure. So the pressure is to be adjusted. It is to be controlled. And that is why we are using a gas flow controller. So this will regulate the flow. It will regulate the pressure. And the gas will enter the injection port. And you can see there is a syringe. It's a microliter syringe. We are going to inject the sample into the injection port. And the injection port, I told you, is at a high temperature. As a user, you have to optimize what is the temperature required depending upon the type of sample. Different samples will require different injection temperatures. That all you have to optimize. So what will happen at this temperature, sample will get converted into vapor. And your gas is also there. The gas is coming from the cylinder. So both your sample vapor and the gas will mix together and will go to the column. Column means it is a stationary phase. And the column is inside an oven. I told you it is to be separately heated. And then one by one, the compounds will start coming out of the column. It will come to the detector. You can see that the detector is also independently heated. And the detector is going to give a signal that is going to be processed by your data processor. This is the same way, same diagram. It's a little more elaborate, that's all. Additionally, what you see in this slide, you can see a carrier gas cylinder that is connected to the injection port that you had seen in the earlier slide also. So carrier gas is always connected to the injection port. Now in the second slide, you see another 2 or 3 cylinders more. One is there is a hydrogen cylinder, there is a makeup gas cylinder, there is an air cylinder. And if you all the three cylinders, we can see they're all connected to the detector port. Only your carrier gas is connected to the injection port, and the remaining three gases are connected to the detector port. And those three gases are called detector gases, or they are also called auxiliary gases. So we have an auxiliary gas system in the GC. We have a carrier gas in the system in the GC. Carrier gas is connected to injection port. Auxiliary gases are connected to the detector port. Why this hydrogen and air and all is required, you will understand when we go forward. And the extreme right hand side, you can see the oven. We have opened the oven. That is, the oven looks like that. The column is always connected inside the oven. It always remains inside the oven because the column is to be heated. And that is why we are using an oven for heating. So independently, we are heating the injection port. We are heating the column oven, and we are also heating the detector port. All the three are independently heated. Okay. Now, this is a very, very important slide for entire type of chromatography. Whether you talk about GC, whether you talk about LC, any type of chromatography, what is the mechanism by which you are getting the separation? Let us take an example, a sample which contains only two different chemical compounds A and B. It's a binary sample. And when you are injecting this sample into your HPLC system or a GC system, ultimately what you are getting two different peaks. Because chromatography, each compound is represented by a chromatographic peak, a triangular peak. So you got two different peaks coming at two different times. That means you are able to separate these two compounds successfully. Maybe if the first compound, the first peak is appearing at 5 minutes, second peak is appearing at 10 minutes. That means there is a wonderful separation between these two compounds, and you are happy. You are able to separate both the compounds present in the given sample. Now the question is how this separation has taken place. Why these two compounds are coming at two different times? That can be explained on the basis of mechanism of zone migration. When we talk about what is mechanism of zone migration, so I'll just read the sentence. Chromatography separation is due to the differential migration rate of components in the mixture. That means, a very simple term I will explain. You have a binary sample. That means you have two different compounds present in there, chemical compound A and chemical compound B. And you want to separate it by a suitable chromatographic technique. Now you are introducing the sample into the column. That is your stationary phase. What is a stationary phase? The stationary phase is also a chemical compound. Stationary is also nothing but a chemical compound. So when your sample goes inside, there will be a lot of physical interactions. That's why I told you the first sentence, there is no chemical reaction, only physical interactions are present in chromatography. So when my sample goes inside the column, which column contains a stationary phase, which is a chemical compound, there will be some physical interactions between the sample compounds A and B and the stationary phase. Now assume that out of these two compounds A and B, compound A has got a liking for the stationary phase. They like each other. The stationary phase and compound A, they like each other. Whereas compound B does not like the stationary phase. I mean, say in a day, everyday life also, we come across so many people. Some people we like, some people we don't like. That can happen. Similarly, when this sample has gone inside, the compound A likes the stationary phase, whereas compound B does not like the stationary phase. So if something is, so compound B, what will happen? It doesn't like the stationary phase. So it doesn't want to spend too much of time there because there is no liking, there is no affinity between them. So it wants to come out faster, so it will move faster. Whereas compound A has got a affinity, it has got a liking for the stationary phase. So it will try to remain there for little more time. They want to be together for some more time because both of them like each other. So what ultimately what will happen? Because the compound B does not like the stationary phase, it wants to come out faster. It will move at a faster speed, faster velocity. Whereas compound A will move only slowly because it wants to spend more amount of time with the stationary phase because both of them like each other. So there is a difference in the degree of affinity, degree of liking between these two compounds and the stationary phase. And due to this difference in the degree of affinity, both these compounds are moving at two different speeds. So there is a difference in the migration rate. And the one which does not like the stationary phase will move at a faster rate and it will come out of the column first. And the one which has got a larger degree of affinity will move slowly and will come out of the column at a later time. I mean, after some time. So that is why these two compounds are coming out at two different times. So why the sample components are separated in chromatography is essentially because of the difference in the degree of affinity between each type of sample component and the stationary phase. Okay. And what is the mobile phase doing here? Mobile phase, in the case of GC, it is doing a postman's job. What is the postman doing? He will go to the post office, collect all the letters and come all the way to your home and deliver the letter at the doorstep. That is all. Other than that, he has no role to play. See, that is what exactly your mobile phase is doing in the case of GC. Collecting the sample compounds from the injection port, traveling to the column, taking it along with the column, and then finally it will come and deliver at the detector. That is all. Other than that, mobile phase has nothing to do with separation. So mobile phase is an inactive component in the case of GC. Please remember, this is a major difference between GC and LC. Whereas in the case of HPLC, your mobile phase is also a very active component. Sometimes mobile phase can influence the separation. It can sometimes revert the separations. Whereas in the case of GC, your separation is not at all affected by mobile phase. It is totally inactive. So there are only two things you have to look at, your sample and your stationary phase. For the case of HPLC, you have to look at three things: your sample, your stationary phase, that's a column, and also the mobile phase, because that is also very, very active there. So that's a major difference between an LC and GC. And general chromatographic equation, when your sample is introduced into the column, and you have a stationary phase inside the column, and there is a mobile phase continuously moving, flowing to the column. So your sample component is going to get distributed between the stationary phase and the mobile phase. So what is happening? Your sample, suppose X is the molecule. Okay, X is the molecule. When you are introducing into the chromatography system, your molecule X will get distributed between the mobile phase M and stationary phase S. So here what is shown is XM is the molar fraction of your sample in the mobile phase, and the right hand side what you see is XS is the molar fraction of the sample in the stationary phase. So at any point of time, there is an equilibrium between these two molar fractions in the mobile phase as well as stationary phase. Now, how will you take it out? You need to take out the entire sample from the column. The basic thumb rule in chromatography is what goes inside has to come out totally. That's a thumb rule. What goes inside the column has to come out totally. So to take it out, you need to optimize the conditions. So you have to optimize the condition in such a way that you are going to shift this equilibrium from the right hand side to the left hand side. That means you are taking out the sample from the stationary phase and bringing it to the mobile phase so that it can flow out of the column, go to the detector and gets detected. That is your optimization process. So every sample needs to be optimized. Conditions are different, columns are different, parameters are different. There is a lot of optimization work involved in chromatography process, whereas in the case of spectroscopy, that much optimization is not required at all. So that's a major difference. So when you talk about, see, this is what is a column is shown. We are injecting a sample which contains three different compounds. Each compound is shown by a separate shape. One is a triangular shape, one is a spherical shape, and one is a sphere. Okay. So you can see initially when you are introducing the sample, all the three compounds are present in the sample. Now, and then your mobile phase is coming, and that is also taking the sample to the column. Now you can see all the three compounds, the triangle, the square and the sphere. One is green, one is three different colors. And you can see the triangle represented compound is at the front, and the circle represented compound is at the extreme backside. What does this show? That means the triangular compound has got the least affinity towards the stationary phase. That is why it is moving faster. It wants to come out first. Whereas the compound represented by a green circle, it has got a very high degree of affinity towards the column. It wants to spend more amount of time with the stationary phase. That is why it is moving slowly and it is at the backside. And the square shaped compound has got an affinity between these two, between the triangle compound and the spherical compound. It is so all the three compounds are moving at three different rates. They will be coming out of the column at three different times, and you will be getting three different peaks at three different times. And the time at which the compound is coming out of the column is called the retention time. So that means the first compound is coming out after, say, for example, 5 minutes. We say the retention time of the first compound is 5 minutes. That means that particular compound has spent 5 minutes inside the column, and after 5 minutes it has come out. The second compound may come after, say, 15 minutes. Third compound may come after 20 minutes. So the three different compounds are coming at three different times because their interactions are different inside the column. There is a degree of difference in the affinity between these compounds toward the stationary phase. That is the very basic thing why these compounds are getting separated by the column. So when I talk about a sample which contains two compounds or three compounds, it is very easy for us to optimize. Imagine a sample which contains something like a perfumery compound. Most of us are putting perfumes, especially when you're going for a function, going for a marriage, going for a get-together. You may put a lot of perfumes or spray and all fragrance. And imagine all these fragrance compounds, all these perfumery compounds are extremely complex samples. Sometimes if I inject a 0.2 microliter of a perfumery compound into a high resolution capillary column in GC, we get sometimes more than 150, more than 180 peaks sometimes we get. That means the perfume what we are using is a mixture of 100 or more than 100 different chemical compounds. And if I need to separate all these 100 compounds on the baseline, that means ultimately, what does it mean? All the 100 compounds have to move to the column at 100 different speeds. Otherwise, if two compounds are moving at the same speed, they will not get separated. They will come out together from the column. And that is what is in chromatography, what we normally call as the peaks are not getting separated. Co-elution is called co-elution. Co-elution means two different compounds are coming out of the column at the same time. That means my column is not able to separate these two compounds, or the conditions you have selected is not sufficient enough for the separation. So you have to do a lot of optimization for this. That is why GC separations are all very, very powerful today. I told you when some of the very difficult compounds, naturally occurring compounds, medicinal oils, very complex hydrocarbons, they all can be separated. That is where the column selection becomes very, very important. When so many columns are available, you should know what type of a column you have to use. You should know the column chemistry and you should know the sample chemistry. And there has to be a proper match between these two. Otherwise, you will not get the desired separation in a chromatography process. Partition coefficient, just looking at the time available to me, I will not be spending too much of time. Partition coefficient, because as I told you, when the sample goes inside, it is going to be distributed between the stationary phase and mobile phase. Partition coefficient represented by Kd is it is the molar fraction of the sample in the stationary phase divided by the molar fraction of the sample in the mobile phase. I will show these are the things better than. It's also called distribution coefficient, ratio of analyte concentration in the stationary phase and mobile phase. So partition coefficient or distribution coefficient, K is equal to Cs by Cm. Cs is the concentration of the molecule in the stationary phase, divided by Cm is the concentration of the molecule in the mobile phase. So that's called the distribution coefficient. or sometimes we also used to call it as a partition coefficient. Then what is the retention factor? There is another important parameter you should know. Retention factor. It is represented by small k. Because your partition coefficient is represented by capital K, retention factor is represented by small k. Retention factor gives an idea as to how long the compound can be retained by the column. If you inject a sample, introduce a sample to the column, how much time the compound will remain inside the column, that information will be given by retention factor. So another measure of retention. So if the compound is going to be retained inside the column for a longer time, you will always have a large value for retention factor. Ratio of the amount of time a compound spends in the stationary phase and mobile phase. And there is a very simple equation. You can calculate K is equal to TR minus TM by TM, where TR is the retention time, TM is the retention time of an unretained peak divided by TM. So that gives a retention factor. Previously it was also called capacity factor or partition factor. So if somebody is telling retention factor, somebody is referring to capacity factor, or somebody is referring to partition factor, they're all same. So different, but nowadays we call it as retention factor. Then there is something called phase ratio. Phase ratio can be used to find out which is a suitable column for a given sample. Phase ratio means ultimately it refers to the amount of stationary phase inside the column. And if the column has got a large amount of stationary phase, your compounds will be retained for a longer time. And then the reverse can happen if the column has got very low amount of stationary phase, your compounds will come out faster. So there is something called phase ratio, which is represented as beta. Beta can be calculated by a simple equation, R divided by 2 into df, where R is the column radius in micrometer. Radius of the column in micrometer divided by 2 multiplied by df. Df is the film thickness. Especially this is referring to when I say film thickness, I am referring to a capillary column. Because inside the capillary column, which you are going to see in detail, the stationary phase is coated as a very thin film having a certain thickness. That is why we call it as film thickness. So there are different columns having various film thicknesses. That means depending upon the film thickness, the stationary phase amount also can vary inside the capillary column. So beta can be calculated by R divided by 2 into df. So if I want to analyze a very highly volatile sample, the sample should be retained for a sufficient amount of time. Otherwise, all the compounds will come out together because they are all having very, very low boiling points. So there should be more retention inside the column. For more retention, you require more amount of stationary phase. And if more amount of stationary phase inside the column, your beta value will be low. So for a highly volatile sample, you have to choose a column whose beta value is low. And the reverse, for a high boiling compound sample, high boiling compound, you have to use a column where beta value is high. So beta value, that is the phase ratio value, will be very useful to you in deciding what type of a column is to be selected for getting a proper separation of the given sample. Then evaluation of GC columns is very important. Especially, please understand, column is a consumable item. It's not a permanent thing. So once you purchase a column, at one point of time, you'll have to replace the column also by a new one. So there is, so how will you decide? When the column is brand new, it will be very efficient. And after using the column for quite some time, the efficiency of the column is going to come down. And at one point of time, you have to throw it out and go for a new one. So what is maybe column efficiency? This is a very common term you will hear. People will tell, my column is very efficient. Or a vendor will come and tell you, sir, I can give you a column, is a very, very efficient column. So what is maybe column efficiency? Column efficiency is nothing but the sharpness of the peak. In the chromatography, when you're analyzing a sample, you want very, very sharp and narrow triangular peaks. Your peak should not be very broad. You don't want a broad peak. And because the peaks become broader, our reproducibility can be a major problem. So we need very sharp and narrow peaks. A column which gives a sharp and narrow peak is always called a more efficient column. Okay, so that is efficiency of the column is related to sharpness of the peak. So then there has to be a variable for that. And what is the variable by which you can express the efficiency? There are two variables. One variable is called n value, number of theoretical plate. Another one is called HTP, height equivalent to one theoretical plate. What is number of theoretical plate? If you open the column, you will not find a plate. There is no plate inside. Then why it is called number of theoretical plate? It's an imaginary concept which has been taken from the distillation process. If you go to huge, big companies, petroleum companies or petrochemical companies, you'll find huge distillation columns there in their plant. And they're actually distilling crude petroleum products, which is a very complex mixture of different hydrocarbons having different boiling points. And they're trying to separate all these hydrocarbon fractions on the basis of difference in boiling point by distillation process. And when you're distilling, actually it's getting heated and the components will start evaporating and they will rise. And inside the column, at regular intervals, plates are constructed. There are plates available, are built into the column, into the distillation column inside. And these vapors will go and condense on one plate for some time. Again, the temperature is increasing. From there, again, it will evaporate. Again, it will rise, go to another plate. There it will get condensed. And this process of condensation, evaporation will take place multiple times. And then the process, different components can get separated, can be taken out. The same process, the same concept is imported into chromatography process. So when I say number of theoretical plates, there is nothing but plate inside the column. So imagine a column, for example, consider an HPLC column, a silica column, which is an adsorbent material. Silica is an adsorbent material. The moment you inject the sample, the silica contains a lot of hydroxyl groups, active hydroxyl groups, selenol groups, SiOH groups. And the compound will be adsorbed by the first available hydroxyl group. But that cannot remain there permanently because the mobile phase is also coming and pushing it. And after some time, it gets dissolved from that. Move forward, another hydroxyl group will absorb it. Again, it will get dissolved. So the process of adsorption and desorption steps are getting repeated multiple times inside the column. So for a layman to understand what is meant by number of theoretical plates, it is nothing but the total number of adsorption, desorption steps taking place inside the column. That is called number of theoretical plates. Otherwise, there is nothing like plate inside. It's an imaginary concept. More number of times these adsorption, desorption steps are getting repeated inside the column, more will be the efficiency of the column, more sharpness of the peak, and better resolution. So that is how a column which has got a very high value for n is considered as a much better, more efficient column. So there are ways by which you can find out the n value for the column. It's a part of software also. And when I started my career, these type of facilities were not available in the software. We used to calculate it manually with a foot rule and pencil. We used to do this manually. We used to calculate. There is one more term, one more variable called HTP, height equal to theoretical, height equal to one theoretical plate. And you will understand what is that in the next slide. So HTP value should be very low or n value should be very high. Then the column is very efficient. Why HTP value is very low? Because HTP can be calculated by a simple equation like L upon n, length of the column in millimeter divided by the number of theoretical plates. So naturally, if n is going to be more, HTP is going to be less because n is coming in the denominator, L divided by n. So when n becomes more, HTP will become less. So that is why I told you, HTP value should be very low, n value should be very high, then the column is a very efficient column. And over a period of time, when you are going to use the column, the n value is going to decrease. That is an indication, slowly, the n value will decrease. And that is an indication that your column is getting aged. Aging is taking place for the column. And at one point of time, a rough approximation is when the n value becomes around approximately 40% of the original value, you can think of replacing the column. Till that time, you can use the column. Okay, the second variable is called stationary phase efficiency, or it is also called selectivity. And what is the variable? Separation factor, alpha value separation factor. This simply shows the column you have selected, the stationary phase you have selected is able to separate two different compounds having close boiling points or close polarity. And that is what is given by alpha value. That is a separation factor. Alpha value should be always more than 1. It should be always more than 1. If alpha value is equal to 1, that means both the compounds are coming out together without any separation. That means coelution is taking place. And the third parameter is called peak symmetry. The peak what you are getting should be a symmetrical peak. If you look at an isosceles triangle, you know what is an isosceles triangle in geometry, basic geometry. You are dividing an isosceles triangle by dropping a perpendicular. It will divide the peak triangle into two equal halves. So that is called a symmetry. That is called symmetry. Both the halves are going to be equal in width. And your chromatography peak also should be like that. If I divide the chromatography peak by drawing a perpendicular, the peak should be divided to two equal halves. Then I can say it's a symmetrical peak. But many times you don't get this also. In chromatography, many times you don't get this. Most of the time your observation is the second half. When you are dividing the peak by putting a perpendicular, your second half is always slightly wider than the first half. And that is what is known as a tailing peak. And tailing peak is accepted in chromatography to a certain extent. Even USP also accepts tailing to a certain extent. Beyond that, it is not accepted. So there are ways and means by which you can find out, you can reduce the tailing. Tailing should be brought to the minimum possible level. If too much of tailing comes, again, your reproducibility will be a problem. So that is called the tailing factor. For all these, there are methods by which you can find out. And all these parameters are very, very important, especially in pharmaceutical industry also. When we are going for a method validation, all these parameters have a lot of importance, significance. The system suitability parameters, those who are used to that term system suitability parameters, all these will come there. And number of theoretical players can be calculated by an equation N is equal to 16 multiplied by TR by WB square, where TR is the retention time, WB is the width of the peak at the baseline, square is the N value. 16 multiplied by TR by WB square is the N value. So at the moment, don't worry about all this, because nowadays nobody is going to calculate it manually, which as we did long back, many years back. Now everything is available for the software. So so that is, and similarly HETP, height equivalent to one theoretical plane. And I told you H is equal to L upon N, where L is the length of the column in millimeter and N is the number of theoretical planes N value. So when N is more, obviously your HETP value is going to be less. Okay, now separation factor I told you is alpha value. It should be more than 1. And this can be found out by K2 by K1, where K2 is the separation, is the partition coefficient, partition factor of the second peak, by divided by K1 is the partition factor of, or you can call capacity factor. Capacity factor of the second peak divided by capacity factor of the first peak, that is K2 by K1 is the alpha value. And it should be always more than 1. If it is 1, means they are not separating. It's coelution. Linear velocity, of course, this I can skip. Ultimately, you are coming to resolution. What is required is you should get a proper resolution in chromatography. Ultimately, every chromatographer wants a very good resolution, and resolution is influenced by efficiency of the column, capacity factor of the stationary phase, and also selectivity alpha value of the stationary phase. And you can see this is called the universal resolution equation. Resolution is represented by R, and the equation you can see all the 3 terms are coming. N value is coming, alpha value is coming, and K value is coming. That means all the 3 factors are going to influence the resolution. The question is how much resolution we should get when we go for a chromatography separation. What is the minimum acceptable resolution you should think of? Okay, you can see this. I have got two compounds to separate. R is equal to 0. So that means they are coming together. Modified the condition. I get a very, very partial separation. I get a very partial separation. R is equal to 0.5. Am I audible to everyone? Hello? Hello?
Yes, sir, you are audible.
Yeah, okay.
Yes, sir.
So it is a very partial separation, 0.5, not at all acceptable. Further modified, I got R value is equal to 1, which is called 90% separation, not acceptable. Further modified, I got R is equal to 1.5. That is the minimum acceptable level of resolution required, 1.5. If it is more than 1.5, no problem, absolutely fine, no problem. So 1.5 is the minimum level of resolution you should get by optimizing the methods. There are different methods you can use for improving the resolution, changing the mobile phase composition in the case of HPLC, changing the column temperature and ramping rate in the case of GC, changing the composition of stationary phase itself, that means changing the column itself, or sometimes changing the dimensions of the column, using a column of different diameter, different length, all those. So there are so many methods by which you can improve the resolution in GC, but ultimately whatever you do, you should get a resolution of 1.5. Now there is just I'm just skipping this part because otherwise time will not permit me to go. There is a HETP, which is the height equivalent to one theoretical plate. There's an equation to calculate this, that is called Van Demeter equation. A plus B divided by U plus C multiplied by U. A is called eddy diffusion, B is called molecular diffusion, and C is called resistance to mass transfer. And U is the linear velocity in centimeter per second. Each term should be minimized. A should be minimized, B should be minimized, and C should be minimized. Then automatically your HETP will get minimized. That means your column efficiency is going to be very high. So I am, because of my time form limit, I am skipping some slides here. Otherwise, I will not be able to finish. There are a lot of other things we have to discuss. Carrier gas, when we talk about now GC, your mobile phase is a gas. And what type of a gas we can use? We have to use an inert gas. We have to use a very pure gas. Purity is very, very important. The minimum purity that is recommended is 99.99% minimum. And separate grade, pure grade gases are available for chromatography. We cannot use a commercial grade gas. And inexpensive also. The only exception is helium. Helium is very, very expensive, but that is the only one which is recommended for GCMS. But normal GC, people don't. But there are not many gases are allowed in the case of GC. You have got very limited choice. Nitrogen, high purity nitrogen, high purity helium, and high purity hydrogen. These are the three gases available to you. Now, frankly speaking, hydrogen is supposed to be the best gas for GC. That's the most efficient gas for GC. But most of the people don't prefer hydrogen because hydrogen is an explosive gas. Because GC is a heated system. Suppose if there's a leakage inside the column, hydrogen gets accumulated, temperature goes up, it can lead to an explosion. So people don't prefer hydrogen because of safety reason. Next one is helium. Helium is also not preferred. There are very few people using helium in GC because helium is very, very expensive. That is a drawback. Otherwise, it's a very safe gas, but expensive. And what is the next one? People use high purity nitrogen. So when you go to industry also, you'll find most of the time people are using high purity nitrogen as the carrier gas. Okay. And the flow rate also will depend upon different types of columns what you are going to use, the dimensions and all. We'll see that. Columns can be made of, when I say column, I am referring to stationary phase because stationary phase is always inside the column. Columns can be made of one stainless steel. Stainless steel columns are available. They are available locally. In Bangalore, it will be there. In Chennai, it will be there. Mumbai, it will be there. Everywhere, it will be there. A lot of people are packing the column and giving you. They are called packed columns. They normally use either stainless steel or glass. Both are possible. Stainless steel columns are available. Glass columns are available. In fact, glass is a very good material for making column, but only problem is fragility. Fragility means it can easily break. So handling is a problem. Otherwise, glass is a wonderful material. It's a 100% inert material. But the problem is handling. Otherwise, most of the imported capillary columns are made of fused silica. Now, when I say capillary column, because we are going to have only two different types of columns. One is called a packed column, which can be available locally, which can purchase locally also. And the second category is called a capillary column. All capillary columns are imported today. There is no local manufacturer. They're all imported. Okay. So let us see type of columns. Either it can be a pack column. There are lots of lot of local people will do this. Will pack and give you much cheaper. And the length can be from say 0.5 meter to maximum 5 meter. For as far as a local pack column is concerned, maximum 5 meter length is allowed. Normally people use 1 meter or 2 meter. That's a normal practice. 1 meter column or 2 meter column they use. 5 meter is very, very rare. Very rare. And the internal diameter of the tubing, either you are using a glass column or a metal stainless steel column, the diameter can vary between 2 millimeter and 4 millimeter. And these columns are very cheap, maybe 2,500 rupees, 3,000 rupees, or at the most 4,000 rupees, you can get a decent column locally. But then capillary columns are all imported, quite expensive. Starting price will be around 25 to 30,000 rupees upwards. And there are columns which are available whose price is more than a lakh of rupees also. They have to be very judiciously used, very carefully used. And look at the length. The length can start from 10 meter. And today we have columns which are more than 100 meter length. And look at the internal diameter, extremely small diameter columns, 0.1 millimeter. And it can go to maximum 0.53 millimeter. And depending upon the internal diameter, these capillary columns are also falling into three different categories. I will tell you that. So how the selection of column is the most critical thing. All the students should understand, those who are going to do some experiment in GC, and the selection of column is very critical, because I consider column as the heart of the system. You are spending so much of money, say huge investment with a very sophisticated GC, and you must be having a very, very sensitive detector, a very high technique injection sample introduction technique, very powerful software system. All those things are there. But if the column selection is wrong, if you are not selected the right type of column, instrument will not help you. You will not get the meaningful separation. So selection of the column is very critical, and column is that what is going to give you the separation. Detector will not give you separation. Injection port will not give you separation. The column only will give you separation. So that's the most important part of the equipment. So selection of column is very critical. That is why I told you earlier, you should know what is the column chemistry and what is the sample chemistry. There are two options. Either you have to go for a local pack column, or you want to go for a imported capillary column. And when you're selecting the column, what is the stationary phase you want to use? There are so many stationary phases available in GC. So what is the stationary phase that is useful to your sample? And what is the stationary phase film thickness? I told you film thickness means the amount of stationary phase available in the capillary column. There are different thickness columns available, 0.1 micron, 0.25 micron, 0.5 micron, 1.8 micron, 5 micron, different thickness columns are available. So what is the stationary phase film thickness you want for your sample? And what is the inner diameter? There are 0.1 mm diameter, 0.25 mm diameter, 0.32 mm diameter, 0.53 mm diameter. Which column you want? And what is the length of the column? Today we have columns available, capillary columns 10 meter, 15 meter, 25 meter, 30 meter, 50 meter, 60, 75, 100, more than 100. What is the length you want? So you should have a clear-cut idea as to what type of column you have to select. And this is a locally available pack column. I'm showing you it contains a packing. That is why it's called packed column. The stationary phase, most of the time the stationary phase is an organic liquid. It's a viscous organic liquid. And this viscous organic liquid is diluted with the help of a suitable solvent. And it is coated on a solid particle. And this solid particle are known as support material. You can see that support material. Many times they are all silicaceous material, diatomaceous earth, kieselguhr earth. They're all silicaceous material, purified, of course, very, very highly purified silicaceous material. They're called support material. And these powder, they're all in powder form, and they are coated with this liquid. And this coated powder is filled inside the column. So there is a packing. That is why it is called packed column. And all this can be available locally. What you see on the left-hand side, it's a glass column. You can see that white color, what you see is the packing. There's a powder, which is a support material, which is an inert material, which is coated with your stationary phase, which is an organic liquid. And that is filled inside the tubing, the column, and that's a glass column. Similarly, you can get columns made of stainless steel also. So, but the problem is all these packed columns which are available locally, they are not very efficient. You cannot use these columns for very complex separations because look at the peak shape at the bottom, you always get broad peaks in packed columns. That's a drawback. So when your sample is a very complex sample, you will not get the meaningful separation. That is why we go for capillary columns. Capillary columns are all important capillary columns. It can be made of fused silica, but nowadays stainless steel also is coming. More popular is fused silica, capillary column. And you see what is the difference here? There is no packing inside. You can see inside there's a small blue color you can see. It's a coating, the liquid, organic liquid, which is your stationary phase, is coated inside the tubing as a very thin film. And then this coating has got a specific thickness also. That is why we always refer to film thickness. There are different film thickness columns available, starting from 0.1 micron film thickness, and it can even go to 5 micron film thickness. So various film thickness columns are available. Film thickness is more, your stationary phase amount is also more inside the column. So that is why, and these columns are very efficient columns. You look at the peak shape, you get very, very sharp peaks here. So, and all these columns are imported. There is no local manufacturer in our place, in our country. And so nowadays, for very complex samples, people prefer a capillary column. Same expensive. So you have to use it very judiciously. You have to take column care is very, very important. So that is all another totally different topic to be discussed. Okay. Capillary columns are widely used. What are the advantages? You get very, very high resolution. A local column cannot give you this much resolution. Very high resolution you can get. Analysis time can be shorter. That means you can complete the analysis faster. And you can go for very high detection limit. Even a target which is very present in very, very small concentration also can be detected by a capillary column, but not by a local column. So these are all some of the important features of a capillary column. And this is why I told you, depending upon the internal diameter, the capillary columns can be divided into 3 different types. 0.1 millimeter column, 0.1 mm diameter column, 0.25 mm diameter column, 0.32 mm diameter column, and 0.53 mm diameter column. That is, columns having different internal diameters are available. And when the diameter, what you have to keep in mind, when the diameter becomes less, your resolution will be more. Resolution and internal diameter are inversely related. Less the diameter, more will be the resolution. Or if you increase the diameter, resolution will become poor. So they have got an inverse relation. Main types of capillary columns. Capillary columns can be divided into 2 types. One is called porous layer open tubular, it is called plot columns. And another one is called wall coated open tubular WCT column. When I started with this presentation, the first slide was, I told you, stationary phase can be a solid or a liquid. Remember that slide, first slide. And I gave 10% weightage for the solid material and 90% weightage for the liquid material. So when I talk about solid stationary phase, for which I gave 10% weightage, that means your stationary phase is a solid material. And that is what you find in the PLOT column, porous layer open tubular column. You can see inside this red tubing, that's a silica tubing. And inside the tubing, we have put small, tiny particles of solid material. It is not a liquid, it's a particle that is attached to the surface. Small particles, you can see a layer of particles. It is a solid material. So your stationary phase here is a solid material, which is an adsorbent material, like silica, graphitase carbon, some other copolymers. There are different types of materials available for that. And these are all used in gas analysis. So porous layer open tubular column. that is used for normally gas analysis. And rest of the analysis for pharmaceutical analysis, flavor and fragrance analysis, environmental analysis, polymer analysis, food analysis, we require a wall-coated open tubular column. And wall-coated open tubular column, your stationary phase is going to be a liquid. You can see inside the tubing, there is a yellow circle. That yellow patch, yellow color, what you see is the thickness, is the liquid material that is coated as a very, very thin layer. Okay, so that is why it is wall coated. The inside wall is coated with a liquid material as a thin film. That's called WCOT column. And WCOT column is the one which you are going to use most of the time. And PLOT columns you are going to use very, very sparingly only for gas analysis. And what are the stationary phases? Most of the stationary phases are polymeric material. They are mostly polymers. Most common for WCOT columns. Either they can be polysiloxanes or it can be polyethylene glycols. I think a lot of background is coming. A lot of background. Hello. Something is some background noise is coming. Somebody's microphone is unmuted. So, hello. So is it okay now? Yeah, there are a lot of background noise coming, a disturbance. Okay.
Yeah. Now
so
it's
most
okay,
of the time for capillary column, WCOT capillary columns, for stationary phase can be polysiloxane, they are silicon polymers, or it can be polyethylene glycols, PG columns. These are two popular stationary phases available in GC in WCOT column. And PLOT column, we have got adsorbent materials like alumina is there, silica is there, some of the graphitase carbon is there, carbon molecular sieve is there, but they are all solid material. They are not liquids. Now, some of the important, when you talk about a polysiloxane polymer, silicon polymer stationary phase, it has got a backbone of silica, silicon, and oxygen. Oxygen, silicon, oxygen, silicon, oxygen, that is a backbone of the material. And on this backbone, you can put different attachments. And depending upon the attachments, you can make different types of columns from the silica backbone. I put an attachment R. If R is equal to 100% methyl group, R is equal to methyl CH3, you get a 100% methyl polysiloxane column. If R is equal to CS2, 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 CN, you get cyanopropyl modified column. If R is equal to CS2, CS2, CF3, you will get trifluoropropyl modified column. And R is a benzene ring, you will phenyl modified column. So depending upon the type of attachment we are going to connect on the silica backbone, different types of columns are available in GC. So we have got plenty of columns. These are all few examples. I'll show a very prominent example. This is a very commonly used column in GC. It's called by trade name by DB5, RTS5, SPB5, BP5. A lot of trade names available. But when I say that DB5 or RTS5, that 5 stands for there is 5% diphenyl modification on the backbone. So it is nothing but 5% diphenyl modified, 95% dimethyl polysiloxane column. And that 5% diphenyl modification induces a slight amount of polarity. That's why it becomes a slightly polar column. Okay. Similarly, this is a column which has got very low bleed capacity, which highly thermally stable, and these type of columns are normally used for GC-MS analysis. That is why we said DB5-MS, RTS5-MS. The silica backbone is slightly modified so that it becomes more stable, and these columns are recommended for MS operation, GC-MS operation or MS-MS operations. We come to polyethylene glycols, highly polar columns. You have to be very careful with a polar column because their temperature stability is not that high. Silicon columns have got a very high temperature stability. They can go to a very high temperature, but polyethylene glycol columns have got a lower temperature capacity. For every column, there is something called MOT, maximum operating temperature, which you should not cross. and it's available from the literature, available from the column manufacturer. If you cross the maximum operating temperature of the column, you will spoil the stationary phase. It will start disintegrating. That means your column gets spoiled. So if the column has got a maximum temperature of 280, I'm giving an example. Suppose the column's maximum operating temperature is 280, you should never cross 280. And to be on the safer side, you should come up to maximum 270, not more than 270. 10 degrees below the recommended maximum, you are always safe. But if you cross the maximum operating temperature, you will spoil the stationary phase because it starts disintegrating. Less stable thermally than polysiloxane columns. And there are outer columns like wax columns. All these polyethylene columns are normally referred to as wax columns. DB wax, RTX wax, like that. And there is another type of columns, FFAP column, free fatty acid phase column. They are also very, very polar columns. So most of the time in chromatography, the general thumb rule is a polar column is preferably used for a polar type of sample. And a non-polar column is preferably used for a non-polar type of sample. Because like dissolves like, that's a basic funda. Like dissolves like. A polar sample and a polar column, there will be proper matching of polarity, separation will be better. Similarly, when you go for a non-polar sample like a saturated hydrocarbon or something, go for a non-polar column, their miscibility will be better. And this is a common different brands available in the market. I am just skipping this. Sample introduction, we can analyze gas sample, liquid sample, and solid sample. All the three types of samples can be analyzed by this. Gas can be introduced with the help of a syringe, or it can be introduced with the help of an attachment on the equipment, which is known as a gas sampling valve. It's an attachment we have to buy as an accessory. And the help of this GSV, gas sampling valve, we can introduce a very precise amount of gas into the column. But if you don't want to buy that attachment, you can even use a normal gas type syringe, which is available in the market. But then you can do only qualitative analysis, not a quantification. Liquid, no problem. You can use a microliter syringe, Hamilton syringe. There are a lot of syringes available. And the quantity, as I told you, is hardly very, very few microliter, 0.2 microliter, 0.5 microliter. And all it is to be dissolved in suitable solvent. And then you can inject it with the help of a syringe. Okay. Injector, there are two types of injectors available in GC. If you are using a local column, you have to go for a pack column injector. And if you are using an imported capillary column, you have to go for capillary column injector. That is to be decided at the time of purchase of the equipment. Accordingly, the manufacturer, the supplier will configure the system and give it to you. What is the injection modes of capillary column? Today, more and more people are using capillary column. So there are different, when you go for a capillary column injector itself, there are different ways of sample introduction. Split injection method, splitless injection method, PTV injection method, direct injection method, cool on column injection method. There are different types of sample introduction. And this all to be, you have to choose the right type of sample introduction for your sample and depending upon the application. So let us not go into detail because time will not permit me. So one very important sample introduction system is called a split injection method. Split injection method, capillary columns are very thin tubes having like 0.2, 0.25 or 0.3 mm diameter. All these columns can accept a very, very extremely small quantity of sample. The sample quantity is more, it will overload the column. You will not get the separation, you will not get the resolution. So you have to very precisely control the sample quantity going into the capillary column. It can be controlled with the help of a ratio, split ratio that you have to set in the software. And depending upon the split ratio, you can introduce a very small quantity of the sample. Suppose if I keep a split ratio 1:10, if I inject 1 microliter sample, it will be divided into 11 equal parts, and 1 part will go to the column and remaining 10 parts will be thrown out of the system automatically. So only 1 part has gone. 1 microliter I've injected, ratio is 1:10, only 0.1 microliter has gone inside the column. So by varying this ratio, you can vary the amount of sample that is going into the column. This also I am going to skip because the column is inside an oven, and there are two types of operations, isothermal and temperature programming. See, isothermal means you are keeping the column temperature constant throughout the analysis and no change. And programming means you start from a lower temperature for the column and slowly you go to a high temperature of the column. That's called programming method. But if a sample is a very complex sample, you have to go for temperature programming analysis method only. That only will give a proper separation. Detector, what is coming out of the column is coming to the detector. And detector will give a signal. Intensity of signal is proportional to the concentration of sample. Here, one point you have to remember, you have to keep in mind is you are setting the temperature of the detector. This detector temperature should be always more than the final column temperature by at least 15 to 20 degrees. That means your column final temperature is 250 degrees. Your detector temperature should be 270 degrees. That's only to avoid any sort of condensation of the sample inside the detector. If sample condensation takes place inside the detector, detector contamination will take place. You have to call the service person. He has to come and open the detector and he has to clean it. So a lot of problems. So and sensitivity will come down. So that the detector temperature will be more than the final column temperature. And what are some of the important detectors? Number one is FID, flame ionization detector. Then there is thermal conductivity detector TCD, flame thermionic detector FTD, flame photometric detector FPD, electron capture detector ECD. We have mass spectrometer detector MSD, and there are a couple of detectors also. I have not given those. Now, out of these, TCD, thermal conductivity, flame ionization, and mass spectrometer, they are general detectors because they can be used for any type of samples. Remaining three, that is flame thermionic, flame photometric, and electron capture, they are meant for very specific analysis. And those three detectors are called selective detectors because they are used only for selected applications. What is the type of analysis? FID can be used for any type of organic compounds. Any sample which contains carbon and hydrogen, and that can be oxidized in a hydrogen air flame. Now you remember why I have shown you a slide where I have discussed about some auxiliary gases. I have shown you a hydrogen cylinder and air cylinder. That is the use here. When you are having an FID detector, you require a flame inside the detector because the compound is to be oxidized, thermally oxidized. Thermally, it has to go thermal ionization. So you require a small flame. And for igniting the flame, you require hydrogen supply and air supply. That is why those gases are required. And I told you they are all connected to the detector. You remember that slide. And there is a ratio of hydrogen to air, 1 part of hydrogen and 10 parts of air. That's a ratio normally we use for igniting a flame. And so any sample which contains carbon and hydrogen, that means any hydrocarbon type of samples, most organic compounds can be analyzed by FID. It has got a decent level of sensitivity also. And electron capture detector is an extremely powerful detector in GC. Very selective to, it will respond only to electron-negative compounds. Any sample which has got affinity for electrons. Any sample which can attract electrons, for example, halogen-containing compounds. And if these compounds are present in extremely trace level, then ECD can be used. But ECD has to be very carefully used. A lot of precautions are required because it contains a radioactive isotope, nickel-63. And if you want to install an ECD in your GC, you require clearance from ERC because of the presence of a radioactive isotope. FTD is selective to samples containing organic nitrogen or phosphorus. Flame photometric FPD is selective to phosphorus or sulfur or tin containing compounds. And TCD is a general purpose detector. You know, people, all the students I know, you have studied maybe in your degree class or before that, Wheatstone bridge circuit in physics. The same thing is applied here. And we are trying to measure the difference in thermal conductivity between the sample vapor and the carrier gas. It's a universal detector, but the only drawback is it has got very low sensitivity. Any sample concentration less than 50 ppm is difficult to be detected by TCD. That's a major drawback. The FID, this is what FID, most organic compounds can be detected. And this is the oxidation reaction that is going on. CH gets oxidized to CHO plus and electron is emitted. There is a capture electrode above the flame and it captures all these electrons and converted into current. And for igniting the flame, you require a hydrogen and air supply in the ratio 1:10. 1 part of hydrogen, 10 parts of. Okay. There's a lot of FID applications are there. I have seen some of the. I've shown some few examples. If anybody is interested, you can always contact us. We can offer you a lot of applications on any of these. Then electron capture detector is very, very sensitive and selective to electrophilic compounds. Compounds containing halogen atoms, compound containing carbonyl groups, nitro groups. And if these are present in extremely small concentration, that time only we'll use ECD. Otherwise, we will not. It is to be very, very judiciously used. You have to be extremely careful. If you contaminate the detector, it is going to be a major problem. Because even the service person cannot open the detector because of the presence of a radioactive material. Okay, you have to use it very carefully, and you have to use extremely pure, ultra pure nitrogen as the carrier gas. And this nickel 63 is continuously emitting beta radiation. Nitrogen undergoes ionization. N2 becomes N2 plus, and 1 electron is emitted. So there is a continuous flow of electron because of the continuous ionization of the carrier gas nitrogen. So there is in the ECD cell, there is a steady current because electron flow is a steady current. That is what normally we call as the base current. And when a sample containing an electrophilic moiety, say for example a PCB, polychlorinated biphenyl, say chlorine containing compound, extremely trace concentration is coming, but it is a highly electrophilic compound. The moment it comes inside the cell, it will absorb some electrons. So at that point of time, the number of electrons will get reduced. That means the amount of current will get reduced, and it is the reduction of current that we are going to measure in ECD, which is proportional to the concentration of the electrophilic compound. You can see on the left-hand side bottom, you will get a negative peak, but you don't see that negative peak on your screen because it is internally converted and you will get a positive. So it is the reduction of the current that is going to be measured in ECD, which is proportional to the concentration of the electrophilic compound. This is an application organochlorine pesticides, very, very important application in food industry, food chemistry. All these are chlorine containing compounds that present in ppb level concentration. And you can see the response that ECD is going to give. And we have used a DB1701 column, that's a medium polar capillary column for the separation. FPD is selective to phosphorus or sulfur containing compounds. Again, here also there is a flame. And when a sulfur containing or a sulfur containing compound is going to burn in flame, sulfur will give out the characteristic radiation, which is having a wavelength of 394 nanometer. Similarly, when the phosphorus containing compound is going to burn, it gives a characteristic wavelength 526 nanometer. So if I need to find out the sulfur compound, I'll put a sulfur filter between the flame and the detector. Detector is a PMT, photomultiplier tube. So this filter, only the 394 nanometer radiation can pass through and fall on the detector. All other things will be blocked. So I am getting a detection only because of sulfur compound. Similarly, if I want to detect a phosphorus compound, I will remove the sulfur filter, I'll put a phosphorus filter. And this phosphorus filter will allow only 526 nanometer to pass through. All others will be blocked. So selectively, I can detect either a sulfur compound or a phosphorus compound using FD, and the user can change the filter without any problem. And these are some of the organophosphorus insecticides. All these are important in food chemistry, food safety nowadays. And we have used a DB1 column, which is a 100% dimethyl polysiloxane column. And FTD is selective to samples containing organic nitrogen or phosphorus containing compounds. It contains a rubidium sulfate pellet, and it is heated to around 800 degrees centigrade. It has got a very unique property. When any sample containing nitrogen or phosphorus flowing over that, it undergoes an ionization reaction and a negative radical is formed. And that principle is used in FTD, and we can very precisely and selectively and very, very, very efficiently quantify samples. These are all nitrogen containing compounds and very, very low concentration. Most of the time, these are all in ppb level or even sub ppb level concentration. We used a 35 DB35 column, which is 35% diphenyl modified, 65% dimethyl polysiloxane column. ECD, of course, I told you it uses the Wheatstone-Brett circuit. It is measuring at any point of time the difference between the thermal conductivity of the sample vapor and the carrier gas. Universal detector, once upon a time it was a universal detector, but now your mass spectrometer is a universal detector. And TCD is still used in very frequently in the gas analysis field. People who are doing gas analysis, they are using TCD, but only drawback is any concentration less than 50 ppm will be difficult to be detected. Qualitative analysis, normally people, in the case of GC, we inject the sample into the column and keep a certain conditions, and we get the retention time. Then under the same condition, we inject our reference standard and see what is the retention time. If the retention times are matching, then we say compound is scientific. That is called a direct comparison of retention time. Your sample retention time and standard retention time should match within plus minus 0.1 minute. That's a condition. Then that means you can say your compound is identified. If there is a difference more than that, then it is not the same compound. It's a totally different compound. You have to use some other standard. So standards are required for qualitative analysis. Then there is another one called retention index, which normally we use in GCMS. So I'm not discussing that. But most of the time in industry also, people go for a direct comparison of retention time. That is why I told you the requirement of reference standards. You have to, after the analysis of sample, you have to inject standards under the same condition and see whether your retention times are matching. Then only you can say my compound is identified. Otherwise, I have not identified my compound. Okay. So this I can. And similarly, lot of quantitative techniques are available. All these are applicable not only to GC but also to HPLC also. Normalization method, corrected area normalization method, absolute calibration curve method. And under absolute calibration curve method, there are two different methods called internal standard method and external standard method. There are a lot of things to discuss about all this, but at this moment, I will not go into those because time will not permit me. Maybe at a later date, if we are going to be lucky to have one more session, maybe sometime later, we can discuss all those in detail. Some of the applications of gas chromatography, a lot of applications in pharmaceuticals, food industry, environmental samples, fragrance and flavor, paints and polymers, petrochemicals and refinery, fertilizer industry, textile industry, agrochemical industry, clinical applications. There is a long list of application areas. In pharmaceutical, one of the major applications is residual solvents. Once upon a time, it was known as OVI as per USP nomenclature. But USP has changed the nomenclature. OVI stands for organic volatile impurities in basic drugs, API. Now it is changed. Now the nomenclature is residual solvents. It is to be done by GC with a headspace attachment. And what is the headspace attachment? I am going to briefly discuss after this. And that's a major application in pharmaceutical industry. Residual solvents, all the drugs are manufactured by chemical reactions. There may be some solvents coming into the final product, and we need to quantify, identify and quantify what are the solvents very precise. Is a USP requirement. So you need to have a headspace attachment along with the GC for that. Then raw materials and intermediates can be analyzed. The packaging materials can be analyzed. Residual solvents in packaging materials can be analyzed. A lot of applications in pharmaceutical industry. This is a pharma raw material. The headspace injection, this is what I'm going to tell you. I'm skipping this slide because we are going to have few more slides on headspace, gas injection technique, headspace transfer line technique. There are two different techniques available for headspace analysis. One is called a transfer line technique, and one is called a gas-tight syringe injection technique. I will tell you about this later so that I can skip it for the time being. These residual solvents in API, pharmaceutical drugs, class 1 solvents, because all these solvents are divided to class 1, class 2, class 3, depending upon the carcinogenicity. Class 1 solvents are supposed to be the maximum carcinogenic, and they are highly objective solvents. And there are limits for that in USP also. And these are some of the 5 solvents which are specified under class 1, 1,1-dichloroethene, 1,1,1-trichloroethane, carbon tetrachloride, benzene, and 1,2-dichloroethane. And there are limits also in USP. If you refer to USP, method number 467, residual solvents in active pharmaceutical ingredients, you can refer to USP, method number 467. Okay, so you have to have, it's a very little laborious analysis. There are 3 different procedures we have to follow. Procedure A for identification, procedure B for confirmation, and procedure C for quantification. And there are different types of columns recommended for that. Okay, so this is a class 1 solvent which is separated on the baseline. And food and environment, pesticide residues, that is one of the major global problem today. Whatever we eat and whatever we drink, all those contain residual pesticides, extremely small concentration. They can be found out. Residual solvents in packaging materials, flavoring compounds in food. There are a lot of flavored foods coming in the market. So flavoring compounds and the fatty acid composition of edible oils. And this is an environmental application. Pesticide residues in water, drinking water. That's also a very major application. Fatty acid composition of an edible oil, very, very important in food industry. Essential oil, perfumery industry. I tell you, all these are perfumery samples. 0.2 microliter of a sample injected into the column, you can see how many peaks are coming. More than 150 peaks sometimes you get. And then this can be separated only by a capillary column, not by a local column. That's the importance of your capillary column. And briefly discussing about GC headspace, because I've taken this topic because headspace is a very, very important attachment for GC today. GC has got a lot of other attachments also, but I have specifically taken headspace because in pharmaceutical industry, not only in pharmaceutical industry, various industries, headspace is a very, very major attachment accessory for GC. Gas chromatography is an excellent separation technique for volatile compounds. That is what we were discussing till now. Headspace sampling is a technique for the analysis of volatile compounds in a non-volatile matrix. Very simple definition. Analysis of a volatile compound in a non-volatile matrix. Your sample is a non-volatile sample. You cannot directly inject into this capillary column, into a GC. It will spoil your equipment. It will spoil your column. It will spoil your injection port because sample is totally non-volatile sample. But that sample contains some volatile fragments. I need to find out, I need to understand what are those volatile components present in the sample. Then this is the only way. You have to have a GC headspace analysis. It's essentially an injection technique. A simple example I will tell you. Blood analysis, alcohol in blood. People consume alcohol. A lot of people, they consume liquor. And once you consume liquor, once you consume alcohol, after some time, this alcohol will come in the bloodstream. By taking out a small quantity of the blood, maybe around 1 ml of blood, and if you try to analyze it by GC headspace, you can precisely find out whether the person has consumed alcohol and how much alcohol is in the bloodstream. It's a major forensic science application, especially if you go to Gujarat, which is a dry state. I had gone there a couple of many years back. There are multiple GC headspace systems which are continuously working on alcohol in blood, samples taken from public servants, public government employees. They are trying to find out what is the alcohol content, whether a person has consumed alcohol or not. It's a forensic application. I'm just giving an example of it. So similarly, a lot of areas we have got wonderful applications for headspace. So it is nothing but an injection mechanism. So now we know there are different types of GC injection, split injection, splitless injection, wide bore capillary column injection, cold on column injection, PTV injection. I just showed you one slide. Similarly, there is another headspace injector and pyrolyzer injector. 2 more. Headspace injector is what we are going to see. That is basically for a volatile compound in a non-volatile sample. And what is pyrolyzer injector, which we are not going to discuss? Pyrolyzer injector is only for polymer analysis. A polymer cannot be directly analyzed by GC because polymer is a very, very high molecular weight compound. It cannot be directly analyzed by GC, out of question. But then if we have this injection technique, pyrolyzer, what we can do, we can analyze a polymer and we can find out what is the polymer composition. In the pyrolyzer, the polymer will get degraded. We are going to thermally decompose the polymer, and so that all the monomers will get generated. And these monomers are all volatile. They'll be sent to the column with the help of a capillary transfer line. And once you get a monomer composition, we can get what is the polymer material. So that is called pyrolysis. That is basically popular in polymer industry and polymer chemistry. So procedure for headspace injection, a sample is placed inside a vial. That's a standard universal vial, 22 ml vial, made of thick glass, thick walled glass, because there is going to be pressure formation inside. The vial should be able to withstand pressure. So that's a special thick walled glass is there, 22 ml capacity. And we take a small amount of sample. It's a liquid sample, about 1 ml of sample. Or say powder sample, we take about 0.5 gram to maximum 1 gram of sample. That's all what is the sample quantity required. And then this vial will be sealed with a rubber septum and aluminum cap. That means the vial is going to be totally sealed after taking the sample. And then this vial is going to be heated inside the headspace attachment. And when the sample is heated, your sample is a non-volatile sample, but it contains some volatile fragments. These volatile fragments will vaporize, will get converted to vapor, but the vapor cannot escape because the vial is totally sealed, and these vapors will get accumulated inside the bottle. And after some time, a certain quantity of the vapor can be automatically transferred into the GC column. You are only transferring the clean vapor, not the sample. And that is not a headspace injection. And what is the advantage? Your column is not get contaminated, injection port is not get contaminated. So these are the, and your analysis becomes sensitive, analysis become faster. These are the conditions, these are the plus points. Features of HSCC, that is what I told you now. It's a very basic thing. I just want to show you one slide. This is a basic theory of headspace. So when you're having two different compounds, the sample is the liquid form, and you are going to heat the sample, your volatile fragments are going to vaporize. Okay. Now, when it is going to vaporize, the sample gets converted into vapor form. There is a requirement. The simple requirement, simple equation, Pi is equal to Pi0 multiplied by Xi multiplied by gamma I. What is Pi? Pi is the vapor pressure of the component I. Vapor pressure of the component at the study. That's the target component. And the vapor pressure of your component depends upon three factors. One is Pi0, that is saturated vapor pressure. Second one is mole fraction in the solution. And third one is the activity coefficient, which is a physical chemistry coefficient, kind of constant activity coefficient. Okay. Now, if we can maximize Pi0, if we can maximize Xi, and if you can maximize gamma I, and then ultimately your Pi can be maximized, that means you can take out the sample in larger proportion into the vapor form from the liquid form. Okay, so now when you are having a headspace injection, don't think that the entire amount from the solution can be taken out into vapor form. That is not possible. That is why the equilibrium is shown. When the equilibrium is attained, the number of molecules coming out from the liquid form to the vapor form will be exactly similar to the number of molecules going back from the vapor form to the liquid form. That's why there is a two-directional arrows we have put. It's an equilibrium. Number one, how many number of molecules are coming out in the vapor form will be equal to that number of molecules going back to the liquid form. So that is, and then with the help of standards, we can quantify, we can precisely quantify the components by headspace analysis. Now, all the three parameters have to be optimized and maximized. Pi0 is to be maximized, Xi is to be maximized, and then the last parameter gamma I. So Pi can be maximized by different, if you increase the temperature, your Pi can be maximized. Taking more amount of sample quantity, your Xi fraction can be maximized, and using an external solvent, you can gamma I can be maximized. So ultimately, your Pi will get increased, but your vapor pressure of the component will increase, and then the sample can come out of the system. And there are three types of headspace technique. One is called static headspace, which is most commonly used. Then second one is called dynamic headspace, and third one is called SPME, solid phase micro extraction. As I heard about this name, SPME, solid phase micro extraction. So there are three types of headspace techniques. And under the static headspace itself, that is the one which is most commonly used, There are three different types: syringe type, balance pressure type, and pressurized loop type. Because I will not be going into those, because this itself is can we have a one-day discussion on headspace, so time will not permit. So there, please understand there are different methods, different types of static headspace: syringe technique, balance pressure technique, pressure loop. So syringe technique, we are transferring a certain amount of vapor from the bottle into the GC with the help of a gas-tight syringe. That is why it is called a syringe technique. And in balance pressure technique and pressurized loop technique, we are transferring a certain quantity of the vapor from the bottle to the GC column with the help of a transfer line, fused silica tubing transfer line. There we are not using a syringe. So in one mechanism, we are using a syringe. Other two mechanisms, we are using a transfer line. So one is called a transfer line technique and one is called a syringe technique. Nowadays in pharmaceutical industry, as per USP requirement, we are using only transfer line mechanism in GC headspace in pharma industry. In non-pharma industry, of course, they can use whatever they want, whether they want to use a syringe technique or a transfer line mechanism. And what are the benefits of static headspace? Sample introduction, compounds diffuse into a gas phase within a sealed vial until the equilibrium is reached. So you have to optimize two different things. One is the temperature, optimum temperature. What is the temperature? Optimum temperature that is required, equilibration temperature, that you have to optimize. So you have to do a lot of trial and error. You have to try different temperatures and you have to find out what is the optimum temperature that you need to optimize. So number one, equilibration temperature. Second thing is how much time you have to maintain the temperature. That is called equilibration time. Suppose your equilibration temperature is 80 degrees. That's the optimum temperature you found out. Now this 80 degrees centigrade is to be maintained for how much time? 10 minutes, 20 minutes, 30 minutes, 40 minutes. That also you have to optimize. So that means you have to optimize the temperature. You also have to optimize the time. That's called equilibration temperature optimization and equilibration time optimization. These are the two things you have to optimize. Okay. And you are only transferring the clean vapor to the GC column. So your non-volatile sample is not going inside. So what is important? What is the benefit you are getting? Injection port is not getting contaminated. Column is not getting contaminated. Analysis time will be shorter. Sensitivity of analysis will increase. So these are some of the, and it has got lot of applications. Pharmaceutical industry, perfumery industry, food industry, lot of areas, even environmental analysis, a lot of areas where forensic applications, clinical applications, lot of areas where you can have a GC headspace attached. So GC, the headspace can be attached to normal GC. It can be attached to GCMS. It can be attached to GCMSMS also. So very major application for that. And then what is the dynamic headspace? This is also a headspace analysis, but this is not very frequently used. It is to be used only for extremely trace amount of concentration of the target, which you cannot even detect by static headspace. Then only you'll go for dynamic headspace. Dynamic headspace is popularly known as DHS, dynamic headspace. Utilizes purge and trap method. The basic fundamental is we are using a purge and trap method in dynamic headspace mechanism to collect and concentrate the target. Your target concentration is extremely low. Sometimes you can even go to PPB or PPT level. PPT levels of concentration. So normal static headspace will not be able to analyze it because sensitivity is so poor, because the concentration is so less. You cannot even employ a static headspace. You have to go for a dynamic headspace. Dynamic headspace is what is, it is employing an in situ concentration. You are concentrating the target over a period of time. Purge and trap. You are purging the target out of your sample and absorbing it of an adsorbent tube. And thereby you are doing an in situ concentration. You are actually concentrating the target component on a trap. And finally, after some time, whatever is absorbed in the trap is dissolved by heating and sent into the GC column. So the sample is purged with a gas. Normally, so same way you take the sample in the bottle and you start heating, And when the heating is taking place, the vapor is getting generated. In static headspace, that vapor is kept there for some time, and after that, the portion of the vapor is directly injected to GC. That is what we normally do in static headspace. But in dynamic headspace, when you starting the heating, the vapor is going to be generated, and this vapor is continuously taken out with the help of a purge gas. And then whatever is coming out of the bottle, glass bottle, is passing through an adsorbent material. That is called a trap, adsorbent material. So the sample gets adsorbed there. And this has to continue for a certain time that you have to optimize. And this trap is kept at a low temperature because at low temperature, adsorption efficiency is very high. So what is happening? The trap is getting enriched in situ concentration of the target material. And after a certain period of time, the purge gas is cut off and the trap is suddenly heated at a very, very fast heating rate. And whatever is adsorbed inside gets dissolved and it goes to a column. And what is the plus point? You get almost 100 times more sensitivity than static headspace. Okay, the adsorbed target material is dissolved by heating the trap and introduced to the GC column. So that is what are the capabilities of dynamic headspace. Continuously, it is sweeping the headspace of a sample with the help of a purge gas. Analytes are concentrated onto an adsorbent trap, adsorbent tube. And finally, the trap is heated and the process can increase sensitivity of almost 100 times more than a static headspace. We have developed a lot of methods in our Shimadzu lab also. Once upon a time, there was a company from Chennai, I suppose. They are making contact lenses for us to use contact lens. And this contact lens, after manufacturing the contact lens, they are all sterilized by ethylene oxide for sterilization. And ethylene oxide, is a carcinogenic material. So after sterilization, there is a process by which they try to remove all the ethylene oxide. But still, they want to find out whether any residual ethylene oxide, even to a very minute concentration, is sticking to the glass. And we did this analysis by dynamic headspace method. And then, of course, the glass was not containing any, but then we could even go to PPT levels of quantification. Parts per trillion levels of quantification we did by dynamic headspace. Okay. Applications of dynamic headspace: pharmaceuticals, environmental analysis, food and beverage, forensic applications, plastic and polymers, lot of areas where you can use headspace, dynamic headspace. And this is solid phase micro extraction analysis. And this is a totally different system. You have got different types of probes available. And the probes can absorb the material when it is heated. And then this probe can directly go to the injection board. And whatever is absorbed on the probe gets dissolved and it goes to a column. So that's called the SPMA method, solid phase micro extraction method. That's also a long topic to discuss. Okay. And I think this is the last slide. And as usual, before going, I am going to have a few questions to you. And these are some of the models. The latest model of GC is Nexus GC 2030. A very, very powerful GC system available in the market today, has got a lot of features. That's called Nexus GC 2030. Then we have got another model with GC 2014 and the 14 model GC 2025. So currently we are offering 3 different models of GC. And the latest open model of GC always Nexus GC 2030 has got fantastic sensitivity and very good capability. Lot of advanced features are available in this model, and the cost, of course, will be going to be more. And the other 2 models are also available: GC 2014, where you can use a capillary column or a local pack column, and Nexus 2030 is ideal for capillary column operation. So these are the 3 models available from Shimadzu. And then, as usual, I am coming to the last this thing. And since we are not meeting tomorrow, I will. We have got time, another 10 minutes. So I'll read one question. If anybody can answer, please do that. I want the students to unmute their mic and talk. I will appreciate that. Number 1 question: what are the basic requirements for a sample to be analyzed by GC? If you listen to my talk, all these questions we can answer in not more than 2 minutes. What are the basic requirements for a sample to be analyzed by GC?
So participants, either you can raise your hand or you can type your answers in the chat box, please.
Please be quick because I have only maximum 10 minutes now before I conclude.
Sir, one answer coming in Manu Divedi. He wrote volatile.
Okay, very good. One condition is volatility, very good. And one more.
And Prachi Desai, sample has to be volatile and has to be thermally stable.
Absolutely right. Very good. Excellent. Very correct answer.
Volatile.
A volatile sample, volatility and thermal stability. So these are the two conditions. Very
and
correct answer.
Few people raise their hands. I'm going to unmute them.
But now they know the answer.
Yeah.
So can I go to the second question? What are the two types of gas chromatography and what is the major difference between the two? What are the two types of gas chromatography and what is the major difference between the two? If you remember my first slide.
Please unmute yourself, participants. Please unmute yourself so that you can talk.
If you recollect the first slide I started with, that is the answer. There lies the answer.
GC and GCMS. One answer.
No. GCMS, we are not talking about GCMS. We are only talking about GC. Gas solid chromatography, where we are going to use a solid stationary phase, and gas liquid chromatography, where we are going to use a liquid stationary phase. One is a solid stationary phase, one is a liquid stationary phase.
Yes, sir. Why Prashanti? So a couple of answers coming in. GSC and GLS from Y Prashanti.
GSC and GLC. Okay, correct answer.
Yes, correct.
Correct answer. Very true. Very true.
And Dr. N. Kanagatara, the gas liquid and gas solid, which is
very
correct.
Good. Excellent.
And some others, V. Shinde, gas solid chromatography and gas liquid chromatography.
Very true. Answers are all correct. I'm so happy. List three characteristics of a stationary phase in GLC. Three characteristics of a stationary phase in GLC. Okay, if you don't know, I can skip that. If anybody wants to tell, otherwise I will tell. The answer will lie if we have to listen to what I was talking. Anyway, I will tell. List three characteristics of stationary phase in GLC. First of all, it should have a very high boiling point. Second one, it has a very high viscosity. Third one, it has got a very low vapor pressure. These are the three characteristics of a liquid that can be used as a stationary phase in GC. Okay, I will go to the next question. I am sure people and all the students will be knowing what is maximum operating temperature. Why the maximum operating temperature is important in a column? MOT, maximum operating temperature, is important in a column. I was talking about it when we were discussing about the columns, different columns. MOT. If you are crossing, every column has got a maximum operating temperature.
So one answer coming, sir.
Yeah.
Sunasira Misra. 500 degrees C is the answer.
That's not the question, though. The question has nothing to do with the answer.
I mean, my question is different.
Yeah,
my
the question is
why maximum operating temperature is important. I don't want a figure, 500, 400, 300, no.
There's another answer. It says for better resolution.
Yeah.
It says for better resolution.
Maximum operating temperature. If you cross the maximum operating temperature, your stationary phase will decompose.
Oh.
That means we'll spoil the column. That's why we should never cross the maximum operating temperature. Different columns will have different maximum operating temperatures. So if I give an example also, if the maximum operating temperature of the column is 280 degrees, you should not cross 270 degrees to be on the safer side. The moment you cross maximum operating temperature, your stationary phase will start decomposing. That means your column is going to be spoiled. That is the importance of your maximum operating temperature.
So many answers are coming in, sir. I think you have answered already.
Okay.
Yeah.
Name two important types of capillary columns and what is the basic difference between these two. You're seeing that slide. Name two important types of capillary columns and what is the basic difference.
So one answer coming, porous layer,
yes.
Open tubular,
correct,
and
correct.
wall coated open tubular.
Absolutely right answer. Plot column and WCOTO column.
Yes.
And the difference is in plot column, we have got a stationary phase, a solid material, and in WCOT column, a stationary phase, a liquid material. Okay, correct answer. And what is the number of theoretical plates in a column and what happens to it when a column ages? At least tell me what is the importance of what information the number of theoretical plate gives. Just one sentence answer. Number of theoretical plate means what? It refers to what?
Better resolution. Manu Devedi gave answers.
Sorry.
Better resolution. And
to a certain extent, he is correct.
And Prachi Desai, column efficiency. She told.
Yes, that is the right answer. Number of theoretical plate defines the efficiency of the column. More the number of theoretical plate, more will be the efficiency of the column. So her answer is correct. And what happens to it when a column ages?
And why Prashanti answering? Sharper the peaks.
Shorter the peaks means what?
Sharper the peaks.
Sharper the peaks. Correct. Sharper the peaks. When the column is more efficient, number of theoretical plates more, peaks will be sharp. She is absolutely right. And what will happen when the column ages?
The number of theoretical plates decreases.
Will decrease. Number of theoretical plates will decrease. When the column ages, the number of theoretical plates will decrease and n value will decrease. And peaks will become broader and broader and broader.
And it's going to be less efficient.
Yes, it becomes less efficient. Correct. Very true. And why is split ratio important? I told you about split injection. Why is split ratio important? Why we use a split injection? This also can be a one sentence answer.
And Shiprat gave answer to measure difference in gas flow.
No. If no answer is coming, I'll tell you. Split ratio is important to introduce a very, very small quantity of the sample into a capillary column so that the capillary column will not be overloaded. It is used to control the amount of sample going inside a capillary column. That's all. So by adjusting the split ratio, we can adjust the sample quantity that is going inside. So a column is not overloaded. And the last question, anybody can tell two important quantification methods in GC. And difference between these two that you leave it. At least you tell me what are two important quantification methods in GC. There is a slide about that also. If you remember that slide, you can tell me what are the two important quantification methods. Should I tell? Because nobody is coming to connect.
Someone says FID.
Sorry?
Someone says FID.
FID is a detector. I am talking about what are the quantification methods. Two important quantification methods in GC.
And we've got another answer. It says internal standard method and the calibration curve method.
Internal standard method is very true. Internal standard and external standard. Both are based on calibration method.
The calibration curve method.
Yeah, calibration curve method. So the right answer is whoever has said it is correct. Internal standard and external standard. Very, very two important quantification methods in GC as well as in HPLC also. So these are the questions. So now we have come to a conclusion. So before I conclude, I got a specific slide to show to only students. I mean, that slide is very important for the students. My question was, now we have come to a conclusion. 4 days I was with you. I was so happy that you are all with me for the last 4 days, right, starting from morning to afternoon. And we have learned a lot of things. We got a lot of information. So knowledge, you are creating, generating knowledge. My simple question to students is whether knowledge alone will make you a successful person in life. Talking about success in life, maybe in your personal life or your professional life, everyone wants to be successful. Each and every person wants to be successful in personal as well as professional life. Whether you can achieve this only with the help of knowledge. Knowledge you are getting when you are attending the university, you are attending the college, you are going to a library and doing a lot of reference work, you are talking to your people, talking to your professors, and the knowledge you can acquire from so many sources. By attending these type of training programs, you can acquire knowledge. But whether acquiring knowledge alone will make you a successful person or not, can anybody,
I would say that you need to have practical experience as well, hands-on experience.
So knowledge alone will, as sir was telling, a lot of practical experience also required. So knowledge alone will not make a person successful. Knowledge is, of course, no doubt, it's one of the most important thing you have to acquire, knowledge. And knowledge you have to acquire from different sources. But then there are two more parameters, two more qualities you should have if you really want to be successful in life. That is, one is attitude, second one, and the third one is the skills. And that is what I am going to show in the last slide. So this is a triangle of success. There are three parameters. One is knowledge, one is attitude, and the last one is skill. Knowledge is to be acquired, basic theory, information, facts and figures, description, learning, science, whatever even from by looking at the nature also, you can get a lot of knowledge. You can acquire knowledge from different sources. Absolutely essential, absolutely required. What is the second property? Second, this thing, you should have attitudes. And attitudes are to be cultivated. It has to come from within you. And under attitude, there are so many are there. Self-motivation, self-confidence. You have to be always self-confident. Whatever you do, you say, I am going to do this, I am going to be successful. You have to be very confident about what all things you do. Integrity, honesty, you have to be honest. And that honesty has to come from within you. I cannot come, or your sir cannot come, and your professor cannot come and make you honest. Honesty has to come from within yourself. And optimism, you have to be always optimistic. Pessimism has no place in our mind. You have to be always optimistic. Cooperation, commitment, these are all things, I mean, are very, very important in the corporate world also. When you go to a corporate world, when you are committing something to your boss, you have to stand by what is your commitment. You have to stand by your commitment. Otherwise, you will not be trusted by people. You have to always give a commitment. You have to honor the commitment. Commitment, cooperation, enthusiasm. You have to be always enthusiastic. Learning. So enthusiasm, optimism, honesty, integrity, self-confidence, all these are attitudes which you have to cultivate. You have to cultivate, it has to come from within you. And then the last one is skills, and skills are to be developed. Goal setting, very important. In your personal life, your professional life, you have to set certain goals. To achieve something, you have to set a goal, and then you have to work towards that. Time management is an extremely important quality you have to develop. It's a skill, time management. Especially when you go to the corporate world, you are your own master. Every time, every moment you spend inside the company, you are accountable. You are answerable. So time management, you can say, is the most creative activity in the given period of time. Your time, you have to properly manage your time. And time is the only thing which everyone is given in equal proportion by God. 24 hours, not a not a second more, not a second less. Everybody has got equal proportion of time. And that's the only thing all of us are getting in equal proportion time. And you have to utilize it properly. Time management is extremely important. Reasoning, communication. You have to be very clear in your communication. And then a person who can communicate much better, definitely he can think of going up in the hierarchy. And interpersonal skills, you have to work with so many people, you have to deal with so many people. So you have to develop a interpersonal skill also. So there are so many qualities under skills that are all to be developed. So many qualities under attitudes, they have to be cultivated, and your knowledge is to be acquired. And if you are able to do all this, and I am absolutely sure that each one of you is going to be a successful person in your life, not only in your personal life, but professional life also. And that is what everybody is looking for. And I'm sure all of you are going to be successful. And you fly to success in your life. And that's what I wish. Each one of you is going to be a successful person in life. And with this, I would like to show my contact details. Anybody wants to contact me later for any help, whatever I know, I can share with you. My email ID is there and my mobile number is there. You can note it down. And in future also, if you want any help from my side, whatever is possible by me, I am open to that. And when you are contacting, you have to only give your name, you are from so-and-so place, because I come across so many people. I may not be able to remember everyone. See, please tell me you're from so-and-so, Geetam, and so-and-so, what is a number, what is a contact email ID. Whatever I know, I can share with you. So you can you can note this information, contact information. And if you want to contact my colleagues also, like Maleshwar, Amol, and Madhapasad, so we are all open to that. So we are always, all of you are always welcome. And then with this, I conclude my session. I think I am right on time. It is going to be just 12:15. So over to you, madam.
Yes, sir. That was very enlightening with the triangle of success, sir. So it's really special to have you, sir. Sir, we have a couple of questions in Q&A. Would you like to take?
Please, please. No, not an issue. Please.
So I think
my colleagues are also there. Others are also there.
Yes.
Maleshwar, Madhapasad, they're all there.
Yes. Few are answered by Maleshwar, sir.
Okay.
And if you are there, maybe you can answer them online. Can we separate, Ramesh Gonduri asking, can we separate diastereomers as well as enantiomers in pharma-related products? If possible, could you please elaborate for how to proceed?
Isomers can be separated. Only exception is your optical isomers can be separated. All this can be done. But if it's an optical isomer, we require a special type of column, which is known as chiral column. All other things, all other isomers can be separated by normal capillary columns. You have to choose the right type of phase. But even optical isomers can be separated, but provided you have to go for a chiral column. So chiral columns are available in GC, chiral columns are available in LC also, but they are quite expensive also. But there are so many chiral columns. Chiral separation itself a chapter to discuss. Optical, so all types of isomers can be separated.
Okay. Another question from Dr. Nagendra ji. Can we isolate the sample back after GC analysis? Is there such facility in the GC instrument?
Please come again. Please once again.
Can we isolate the sample back after GC analysis? Is there such facility available with the GC instrument?
Achha, I think what he is referring to is whether we can collect the sample after the GC analysis.
Maybe it's to recover. Can we recover the sample?
Yes, I understand. In the case of GC, that is not possible. We don't have a sample collection facility in GC, but LC it is available. Because LC, there is something called preparative GC, where you can collect fragments. Fraction collector we can use, and then we can collect the samples coming out of LC column. But in GC, that is not possible, simply because how much is the amount of sample you are injecting? Sometimes 0.1 microliter, 0.2 microliter, and many times the sample is already destroyed. The FID, the sample is going to be ionized and is thermally destroyed. Sample collection is not possible in the case of GC, so there is no sample collection. Or that is why we are not talking about preparative GC. But we talk about preparative LC where sample collection is possible. In the case of GC, that's not possible.
Okay, another question from Dr. G. Nagendra again. Sir, what is meant by RP2, RP8 and RP18? What does RP indicates?
That is basically is referring to HPLC column. RP stands for reverse phase columns. RP8 is nothing but a C8 column, reverse phase column, carbon number 8, C8 column, octyl columns. And RP18 is reverse phase C18 column, octadecyl columns. RP stands for reverse phase because in HPLC there are two basic modes of operation, modes of suppression. One is RP, that is reverse phase, and one is NP, that is normal phase. Normal phase, your column is polar, and RP, your column is non-polar. So RP8 and RP18 is C18 column and C8 column. They are reverse phase columns. So RP stands for reverse phase.
And from chat box, I pick one question from my Prashanti. What is the lifespan of column?
That's very, very difficult to answer because it depends on so many factors. Depends upon number one factor is the type of sample. How many samples you are injecting per day? What is the use? How frequently you are using the column? And last one, and not the least one, how much care you take about the column. All this will decide the life of a column. I'll just give you an example. I had gone to a customer long back in somewhere in Gujarat, and that person told me, "Sir, I am changing my capillary column every 6 months. I am changing. Every 3 months, I am changing the capillary column." I asked him why, because capillary columns are expensive. Why you are changing? You are purchasing a new column every 3 months. He said, "I am doing this, sir, not because of passion, but out of compulsion. Because 3 months time, his column is gone because he is manufacturing very corrosive compounds, agrochemical compounds, and within 3 to 4 months time, the column efficiency is gone. He cannot use it. He has to go for a new column because it is the nature of the compound that is more important. And his compounds are all very corrosive type of compounds. So column is getting spoiled within 3 to 4 months time, or at the most 4 to 5 months time. So that is why nature of the sample is very important. On the contrary, if you go to a perfumery company, their samples are more or less very neat samples. A person, I know one customer in perfumery industry who is using a capillary column for almost 4 years without any problem. So it depends upon number one, major factor is the nature of the sample. Second one is how many samples you analyze per day. One person may say, I am only analyzing 3 samples or 4 samples in a day. Another customer will say, I am analyzing 50 samples in a day. So the usage is more. So number of samples per day, that is another factor. And how much care you take about the column. Column is to be taken care of by the user. There is something like column conditioning and all. Of course, time will not permit you to discuss about that. Column conditioning is to be done periodically, so the column is always in a perfect condition always. So all these factors will decide the column life. So it is very difficult to quantify. I cannot tell, okay, person, you buy the column, you can use it for 3 years, 4 years, 5 years. I cannot tell that. It depends on so many factors. This is a question we normally hear from customers when we go to them. It's a very common question. But there is no specific answer. It all depends on so many parameters.
Okay. Sir, one more question from Ramesh Ganduri. Could you see able to separate enantiomers and diastereomers?
That I told you always. I mean, I answered this question. You can separate all these isomers, including optical isomers, but you require, if you want to separate optical isomers, you want a chiral column. Other type of isomers, we can use the normal capillary column.
Okay. And Dashinde asking for molecular weight determination, MALDI mass spectrometry is better or chromatography is better?
See, if you are interested in a single compound, if you have got a chemical compound, if you have got a drug sample, a pharmaceutical drug, and you want to find out the molecular weight of the compound, I will recommend mass spectrometry. In mass spectrometry, there is a mode of operation called positive chemical ionization. And positive chemical ionization in mass spectrometry, you can find out the molecular weight of the compound. But tomorrow, if you get a polymeric material, a polymer, and then you want, and everyone knows a polymeric compound does not have a very clear-cut, well-defined molecular weight. It has got a distribution. We talk about molecular weight distribution, MWD. In that case, you can go for gel permeation chromatography coming under HPLC. Gel permeation chromatography, GPC, or it is also called SEC, size exclusion chromatography, where you can find out the molecular weight distribution of a polymeric material. And a polymeric material has got different molecular weights. Number average molecular weight Mn, the weight average molecular weight Mw, viscosity average molecular weight Mb, Z average molecular weight Mz. There are different molecular weights that can be calculated. Polydispersity can be calculated. Mw by Mn is the polydispersity, how dispersed the polymer is. And we can calculate the molecular weight distribution. So for those compounds, GPC is the best method. But if it's a very single compound like a pharmaceutical drug, mass spectrometry is the recommended method.
Okay, one more question from Prabha. While using column chromatography, we need to use excess solvent to separate and isolate the mixture of compounds. There is any advancement in order to reduce or minimize the usage of solvent?
Minimize this. Nowadays, the column technology has developed so much that too much of salt, because nowadays we are talking about very small diameter columns, even in SPLC also, and the consumption of solvent has come down drastically. You don't have to think of too much of solvent consumption. The flow rate, we are talking about 1 ml per minute flow rate or 2 ml per minute flow rate, and the column size has reduced, 3 centimeter column, and how much solvents? A couple of mLs of solvent only will be required. So solvent consumption has reduced drastically because of developments in column technology.
Another question from Dr. Sheikh Anwar. Requirement of guard column is necessary in GC.
You can do that. There is no harm in that. Like in SPLC also, we put a guard column. So mainly the guard column is meant for protecting the analytical column. In GC also, there are many places where you use a guard column in GC to protect the capillary column. And guard column is nothing but a few silica tubing without any coating that is used as a guard column and meant for protecting your main analytical column, which is expensive. Normally, we put a 5 meter or sometimes even less than that. 3 to 5 meter, only few silica capillary tube is used as a guard column in GC. It can be done. People are using that also. Not everyone, but there are people who are using guard column in GC.
One more question, sir, from Anonymous. What is the use of pyrolysis GCMS?
Pyrolysis GCMS. Pyrolysis GCMS is required for characterizing a polymeric material. I told you when I talked about pyrolyzer, a polymeric material cannot be directly injected into GC column because a high molecular weight compound, totally non-volatile compound. In that case, if you want to characterize the polymer, like a material character, you want to characterize the polymer, we want to know what type of a polymer it is, whether a homopolymer, a copolymer, then I cannot directly inject into GC because it's a totally non-volatile sample. It will spoil my column. But if I have a pyrolyzer, it can be attached to GC, it can be attached to GCMS, it can be attached to GCMS also. And what a pyrolyzer does, you take a very small quantity of sample, few milligrams of the polymer, and put inside the pyrolyzer. Pyrolyzer contains a furnace, and the furnace temperature goes up to 800 to 900 degrees centigrade. And under this temperature condition, the polymer will decompose, and monomers are getting generated. And these monomers are all volatile. And these generated monomers are transferred to the GC column with the help of a capillary transfer line. And then what you get a monomer composition. And once you get a monomer composition, we have some dedicated polymer libraries. And from the monomer composition, the library will tell you this is the polymer composition. So this can be done by GC, but when you go for a GC, problem is there is no library available for GC. But if you go for a GCMS with pyrolyzer, we have a facility of library search. So we can identify what is the polymer composition from the polymer library. Frontier Science, we are giving a Frontier Science library for that. And there are a lot of customers for us who are using this pyrolyzer along with the library. For example, Seat Tires is using a pyrolyzer. So many people are using a pyrolyzer along with the GCMS also. In Delhi also there are customers. In Mumbai also there are customers. Baroda there are customers. And I think even South also I think there are few customers. I don't remember the names, but that is the utility. So if you go for a pyrolyzer with GCMS, you can totally characterize the polymer because we also have a facility for a library search. Optional polymer libraries are available.
Sir, the same person means it's an anonymous question. I don't know. Is pyrolysis GCMS facility available in South India? South India?
I think somebody is using. I think, but I don't remember who is that. I think somebody in South Mangalore side there is a customer. I don't. Unfortunately, you can get this information from Rajshekar because it was coming under his territory, I suppose. Somewhere in Mangalore, there is a customer who is using a pyrolyzer along with a GCMS. That name, I forgot the name because I met that person also. He came to Shimatsu lab in Mumbai, but it was quite some time back. Unfortunately, I don't remember the name. But Rajshekar will be able to give the name who are all using pyrolyzer with GCMS in South India.
Okay, later you can contact Girijan sir on this matter for further information. And Anusuyam is asking what kind of solvents are preferable for heterocyclic compounds?
Any organic solvent in which it is soluble, not an issue.
Sir, there are so many questions in the chat box. Due to time constraint, we cannot take them.
Yeah.
I would like to request participants, please contact and Girijan sir email. He will be more happy to answer to you.
Yeah.
Okay.
Again, I'm showing my contact information.
Yes. And one my personal question, sir. So you mentioned about column conditioning, right?
Yes,
so how often we should do column conditioning?
Column conditioning, you have to decide a frequency. If you are using the column daily, and if you are injecting so many samples, I will recommend at least once in 15 days you have to do that. That is my recommendation. Because we are using the column for so many different samples and different number of samples you're injecting per day. It is ideal if you can condition the column once in 15 days. Once in 15 days. There are people who are doing once in a month also. There are some people who are doing once in a week also. Very good. That's also an excellent. Once in a week you can do in a last weekend of the day. Maybe Friday evening or Saturday evening, you can do that. Wonderful. But at least once in 15 days you should do. Your column will be always in a what you call a very, very conditioned state, and the performance will be very good.
Means the time duration, how long we should do? Means a couple of hours?
No, it's not like that. Conditioning means what you do, suppose your column has got a maximum temperature of say 350 degrees. I'm just giving most of the silicon columns can go to 350 degrees centigrade. So what you do, you connect the column inside the GC, okay, and you make a program. Say you start from say 60 degrees centigrade, and since the column maximum temperature is 350, I will not prefer to go 320. I mean, for conditioning, or 330. Okay. So maximum temperature is 330. Starting temperature is 60 degree. And I am going to start the heating. I am going to start heating at the rate of 10 degrees per minute. That is my rate of heating.
Okay.
So what I will do is start from 60 degree. I'm going to increase the temperature at the rate of 10 degrees per minute, and I will go to 330 degrees centigrade. And the 330 degrees centigrade I will maintain for about 5 minutes. Okay. After 5 minutes, I will cool the column. It will come back to 60. That is one cycle completed. I will run this cycle at least 4 times. Means going to 60, going from 60 to 330, maintaining 330 for 5 minutes, coming back to 60, one cycle. Run this cycle at least 4 times. Okay. And when this heating is going on, what you do, every 5 minutes or every 10 minutes or every 5 minutes, you take 1 microliter of a good quality solvent like acetone or methanol. Okay. Just inject into that column and it will go off. It will for a washing effect. Okay. Every 5 minutes or every 10 minutes, you take 1 microliter of good quality, pure quality acetone or methanol, like that, and that is inject into that. And that column, that solvent vapor also will go out, and it also will clean the column. So this is the proper conditioning cycle. So run this cycle at least 4 times, and then cool it down, and don't switch off the carrier gas before. That is one thing you have to remember. Even the students should remember, before switching off the equipment, you have to see that the column temperature has come to at least 40 degrees. Then only you should switch off the carrier gas. If you switch off the carrier gas when the column is hot, column will get spoiled. So first thing in the GC laboratory, when the moment you enter the laboratory in the morning, first thing you have to start is starting the carrier gas. And the last thing you have to do before you leave the gas is closing the cylinder. Because never close the carrier gas supply, gas flow before that column has come to 40 degrees centigrade. Then once it is 40 degree, you can switch off the equipment, you can shut down the cylinder, and you can leave the lab.
Okay, thank you so much, sir.
Hello, am I audible?
Yes, please.
Yes.
Sir, myself, Dr. Ramesh,
Yeah.
Micro Labs. This was a fantastic workshop, and this was given me like so much fundamentals and principles of main analytical techniques like UV, FTIR, GC. So even I have got many characterization. So daily life I'm using. So I got a very informative stuff from your workshop.
Thank you,
sir.
Thank you, sir. Sir, you are from Micro Lab, Bangalore?
Yeah, exactly. R&D, Kudlu.
Sorry?
R&D Kudlu, yeah, Bangalore, R&D Kudlu.
You are Dr. Ramesh?
Yes.
Okay, sir. Micro Lab is a big customer for us.
Micro Lab. Even I'm, tell me, sir. Yeah.
Even I had come to Micro Lab quite some time back, not recently. Couple of years back, I had visited Micro Lab 2 times for certain presentations, sir.
Yeah, good,
Micro
sir.
Lab
really.
is a major customer for us in Bangalore.
Even I'm using FTIR, UV, Simarju.
I know. So many instruments are there. We have got a large presence in Micro Lab, Bangalore, Micro Lab, Mumbai.
Yes, sir. Thank you so much. And my heartfelt congratulations to each and everyone, and especially organizing team, convener, and coordinator. Thank you, sir. Thank you.
And thank you, sir, for taking your time and attending this webinar. I'm so happy because you are a very, very important customer for us.
Oh my God. Sir, there are so many hands rising to give feedback. Thank you so much, Ramesh Ganduri. That was so nice of you. And now I think many participants would like to give feedback. Maybe we can allow a couple of them.
Yeah.
Now I think I can see why Prashanti.
Yeah.
Prashanti, please go ahead and talk.
Yeah, good afternoon, sir.
Yes, please. You are from?
Heartfelt thanks to organizers and...
Please, I request you, please identify yourself. You are from which college or which industry?
Yes, sir. Myself, Dr. Y. Prashanti, Mahatma Gandhi University, Assistant Professor, Head of the Department of Chemistry and
Mahatma Gandhi University, where in
Nalgonda.
Hyderabad. Okay.
Nalgonda, Telangana State.
Okay.
Thank you very much, sir, for your most sincere thanks to organizers and renowned speakers, especially Dr. Girijan sir and team. And my thanks to organizer, convener of the program, Srilakshmi ma'am, and all the organizers. Really, it's an outstanding session, sir. Totally equipped and learned a lot in a comfortable environment. The style and knowledge of the presenter is amazing. Content was very well presented, sir. It was everything what I was hoping. This was a fabulous session, I feel, because it opens our minds by covering important techniques, very crystal clear and with a good rhythm, sir. Overall, I feel very comfortable and I equipped a lot, sir.
Thank you, doctor. Thank you very much, and thank you for attending this session.
And I
hope to meet you sometime when I come to Hyderabad.
Yes, sir. Thank you, sir. Thank you once again. Thanks to
my colleague from Hyderabad is also present here, Maleshwar. He is from Hyderabad.
Yes, Hyderabad office. Thank you for giving me.
And K. Arunan, I think he's raising his hand. Talk, please, Arunanji. Please go ahead and talk. Please identify yourself first.
Hello?
Yes.
Yes, we can hear you, sir.
Yes, ma'am. This is Arjun from Bharadas University, Tiruchirappalli, Tamil Nadu.
Okay, Tamil Nadu. Okay,
Okay, yes, sir. So first of all, thank you so much for the organizer conducting this excellent workshop mainly without collecting money. Due to this corona issue, this is the best workshop for without collecting money. I really appreciate the organizers, especially one of the madam, I don't know the exact name.
Yeah, Srilakshmi.
So really thanks. Yes, ma'am. Really thankful. As well as this speaker, especially Mr. Hirijan, is delivered the basic and crystal clear idea about the analytical instruments like DGA, DTA, and GL inductors, everything. So once again, heartful thanks to the organizing team as well as Giant University conducting this wonderful workshop.
Thank you, sir. Thank you very much.
Yeah, yes, sir. Future days also is conducting this more webinar, this type of online mode or offline mode. We are welcome to the organizer, as well as thank you so much for the entire team, Giant University.
Thank you, sir.
Thank you, sir. Thank you very much. Thank you very much for the feedback. Thank you. Your feedback is very, very important.
You are welcome to Bhadas University if possible.
Yes, I would like to come, sir. I will like to come. I'm just waiting for the corona to go away. I would like to meet all of you in person.
Okay, sir.
And Manu Divedi, please go ahead and talk. He's one of the active participants, sir. I know. Just now he spoke Arnan also and Manu Divedi.
Yes.
Please go ahead, Manu Divedi. Please unmute yourself. Please.
Hello.
Yes. Yes, we can hear you, madam.
Okay, good afternoon, everyone. First of all, I'm a female.
Okay. We are thinking you are male. Yes, glad to know. Yes.
Okay.
Yes.
So I just wanted to say that this was the fantastic e-workshop which I have ever attended, and the speaker, Dr. R. Girirajan, sir, you are awesome, I would say. Sir, it was fantastic. In fact, I got to know so many new things about GC and spectroscopy. And basically, I use all these things, but few of the things I never cared about. But now I will take care of all those things. So thank you.
Madam, you are from which institution?
Sir, I'm still, I would say I'm still struggling with my PhD.
Okay, yeah. Where you are doing PhD?
Yes, I'm from MS University of Baroda, sir.
Achha, okay, MS University of Baroda. Okay, very familiar place for me. I had come there a couple of times, MS University, Baroda. Okay, so you are doing PhD in what? Chemistry?
Sir, in phytochemistry, sir.
Phytochemistry, okay. MS University is a big customer for us. I had come there once or twice I think, MS University. Yes, very prominent place. Very good.
And thank you, Manu Devedi. It was very, very glad. Then who is it? V Dashinde. Dashinde, please unmute yourself. Yeah, please. Go ahead.
Yeah, ma'am. Good afternoon. Yeah. Good afternoon to all. Myself, Vandana Shinde. I completed PhD. I am at assistant professor at Kavitri Banabai Chaudhary, North Maharashtra University, Jalgaon, Maharashtra.
Wow. Where? Jalgaon.
Jalgaon. Actually, first I would like to thank to all speaker, convener, coordinator, and organizing team. They nicely present their work. Girijan sir very clearly and very basic information given with some case study example that is very useful, because these characterization techniques are very useful. Without characterization, we can't go to the application. That's why this is most important. And I totally enjoyed and learned this workshop. Very good workshop. Lot of things I learned new. Again, some practical technical issues that will be also I received from this workshop from the Girijan sir's team, and therefore lastly I say I very thankful to the Sri Lakshmi ma'am also, very nicely hosting and giving some tips and hints during the queries.
Thank you, ma'am. Thank you.
So my question is whether you are attached to North Marathwada University?
North Maharashtra University, Jalgaon. Previously, it is North Maharashtra University. Now, Kavitri Banabai Chaudhary.
Okay, because NMU I had come couple of times to North Marathwada University, Jalgaon, long back. And then I
actually in our university, University Institute of Technology, UICT is there. There are lots of characterization techniques facilities are there.
Okay.
That's why I used that during my PhD as well as now. Also, I am using for that.
Okay, very good, very good. Good.
So thank you.
Thank you for attending.
Thank you.
Sir, this was a very rare situation because a lot of people wants to give their feedback. Unfortunately, we cannot take one internal feedback we will consider to take from Shiprat. Please talk. Unmute yourself, Shiprat, you there?
Can you hear me?
Yes, yes. Please go ahead and talk.
Yeah, sir. Good afternoon, everyone.
Yeah.
Analysts and speakers, and mainly for all participants. So, me myself, Shiprat, a research scholar in Geetham University. So, from past 3 days, I have been actively participating in this workshop. It was very beautiful, and I got a round figure of information on all like UV, FTIR, thermo, analytical, and almost all analytical instruments like GC 2 days. So I'm focusing on, sir, what you know, almost everyone had said everything, but it was very good of triangular of success theory of yours ending. This surely I will follow, sir, because of this success theory, triangle of success theory may help me in the future. So almost everyone had told everything, but the ending point was very beautiful, like after a meal, like sweet at the end.
And I'm sure you are going to be successful. You will 100% you'll become successful in your life.
Okay, sir. Sure. Thank you, sir. Okay. So that's what I thank for Geetham University for giving a beautiful opportunity to join this workshop, and all the chemistry department and convener and all the team who had worked behind this workshop to get successful. So thank you one and all, sir. And many thanks for Girijan, sir. Thank you for all this informative, knowledgeable information.
Thank you. Thank you. We will meet again.
Yeah, sir.
Yes,
thank
yes,
you.
yes. Sir, with this we can stop taking feedback.
Yeah.
So now, dear participants, with this we come to an end of the 4-day national workshop on modern analytical techniques and material characterization. To recap, in this workshop, Mr. Girjan from Toshwin Analytical Private Limited has covered various interesting topics such as UV visible spectroscopy, derivative UV spectroscopy, multi-component analysis, FTR spectroscopy, various IR accessories such as transmission, DR, ATR, etc., that are used to analyze various types of samples, and various analytical techniques such as thermal analytical techniques such as DTA, DSC, TG to measure the thermal, physical, and chemical properties of the materials, and gas chromatography techniques in which mechanism for separation of components and different parameters for better resolution, etc., are covered in detail. Overall, this is a very in-detail workshop which has covered basics, instrumentation, and application of all the 4 techniques online even in this pandemic period. Now, I convey my heartfelt gratitude to Mr. Girjan, sir, and his team from Toshwin, and delegates to be here today. And most humbly, I thank our management for providing this opportunity to the chemistry department to organize a wonderful workshop. I would like to now convey my warm regards to Professor Subramaniam, Sir, Dean of Sciences Geetham, who join us today, and would request him to address the participants.
Thank you, Dr. Sri Lakshmi. I hope you all can hear me.
Yes, sir. Yes, sir. Please.
Yeah, thank you, Dr. Sri Lakshmi.
Yes.
Mr. Girijan, the participants, I'm so delighted that such a nice conference is organized by Geetham, extending the outreach. Before I go to the details, Manu Dwivedi, when we looked at the name, we got a confusion. And we also got a confusion when we saw the name VDA Shinde. We never knew that it is Miss Dr. Vandana Shinde. We never knew that Miss Manu Dwivedi. That tells what characterization is. You may look at a material. Until and unless the material comes to you and talks to you, you do not know. And I must say, I'm basically an experimental material scientist, got my training in physics. And I don't know how I really thank Mr. Girijan. He touched upon so important aspects like UV visible, FTIR, thermoanalytical, and most important, gas chromatography. My fundamental question whenever we go for UV visible, if you do it for a solid, the visible spectroscopy, what are density of states? If I ask this question, 99% of the students will give me such a blank look. They have no idea about what are the basic principles on which the instruments work. And I must also say, maximum problems come only for the experimental scientists. For example, if you are a theoretician, take a pen and a paper. Even if the pen doesn't write, doesn't matter, they can take a pencil. Even if they don't have a paper, they can write on the wall. Uh, these are the type of flexibilities they have, but we don't have that. For example, I could follow how frequently should I clean my column. That's what I mean. One of the questions in gas chromatography, very difficult to answer, because Mr. Girijan, with his vast experience, he will be able to answer you. So to say, the experimental science is a rarity, and the people who are understanding the basic principles of the measurement are still rare. Under these rare circumstances, when we are finding Mr. Girijan, I would like to call him as the diamond of the characterization community, because it's very rare to get such type of people. I mean, he never. I mean, I have been listening to him over the past half an hour. Probably he has not spoken with his brain. He has spoken with his heart, because he has been working on these characterizations. You wake him up in the dead of the night and ask him, "This is a problem." He has a solution. And I'm so happy that he could spare the time, he could come, he could address almost about 140 participants today. Sir, my sincere thanks to you. And I must say, Geetam is lucky to have you, and all the participants are lucky to have you. And please remember, our relation is not going to end here. Today is the day we wanted to start a fresh, active, and interactive relations with you, because nowadays, experimental science, I mean, this is a fundamental fact. You may find a fantastic theory. For example, Einstein was not given a Nobel Prize for his theory of relativity. You should ask a question, why? Why? Because Nobel Alfred Nobel realized, and the committee realized, until and unless it has been proven by an experiment, the science, it is still a hypothetical science. So Einstein was awarded the prize for what he has observed in the photoelectric effect. Raman was given a prize, Nobel Prize, for his Raman effect. Even if the theories are existing earlier, nobody could claim a Nobel Prize for that. That is the importance of experiment and material characterization. We live in materials. So my sincere thanks to Mr. Girijan, and we welcome you, and probably we should work much closer. Shimadzu is a company which is specializing in spectroscopy. Of course, people like you make it much more valuable. And about the participants, I must really thank you for, I mean, I could see some feedback, which is really excellent. And I must thank Dr. Sri Lakshmi and his team for organizing this. I would like to say this is a jewel in the crown in experimental science, material characterization. And my honest feeling is, let this workshop bring out a small, I mean, I'm going to work with Sri Lakshmi and Mr. Girijan. We should bring out a small book on the basic principles of the characterization techniques have been explained in this workshop. This is not a proceedings of the workshop, but this is going to be the basic philosophy of all the people who are characterizing in this, participating in this. Mr. Girijan, if you agree with me, I would like to work with you.
Thank you, sir. Thank you so much.
So that we can bring out a small volume of about, say, 30-40 pages,
yeah,
on the basic principles of characterization. Okay. So with this, I would like to say thank you very much, and I'm really grateful for this opportunity. And I'm pretty sure Geetam, with more active people like Dr. Sri Lakshmi, will be conducting more webinars which are more useful to all the scientific community. Thank you very much. Thanks a lot.
Thank you, sir. Thank you very much.
Thank you, sir, for inspiring and encouraging words. Now I request Professor Atul Kumar, Principal of Science, JSS, Geetham, Bangalore, to address the participants.
Thank you, Dr. Srilakshmi. Am I audible?
Yes, sir. Yes, sir.
Okay. Good morning, Dean sir, Sudhanu sir. I need to say this that
Hey Atul, you are very feeble. You have to increase your volume.
Okay, is that correct now? Is this okay now?
A little more. You are a young guy. You can really shout.
Yeah, I can. Yeah, sure. Am I audible loudly now?
Yeah.
Yes, sir.
Okay. I really need to say this that this really a great experience for last 4 days, and I've been listening I on and off, and today I've been listening Dr. Giriraj for half an hour, and it was mesmerizing to just hear what he's been saying. Especially I joined when he was discussing the triangle of success for all the participants, which is a wonderful thing to say. I would like to just place on record the sincere thank to Mr. Giriraj from Shimazu and Toshvin. He has taken that much effort and spent around 10 to 12 hours to discuss the material characterization, instrumentation and all that for the budding researcher, scientist and the young assistant professor. It's a really, material science is a great field to study. And it's like discover new materials and they are used in various applications. So application oriented characterization is a great thing. So it's about understanding a basic thing. Like every material possesses various properties like optical, electrical, structural, various kind of instrumentation are used to characterize these material and to see their applicability. So that is a great thing. And Dr. Giriraj and his team have explained lucidly to all the participants, and I'm sure they will be benefited a lot by those lectures. I need to place my sincere thanks to Dr. Srilakshmi, Dr. Vikram Baswa, and Dr. Nagaraju for organizing this excellently organized, flawless, unblemished 8 to 10 hours of this conference. And I'm sure that all the participants are immensely benefited by that. That is a thanks to all the organizing team. A note to all the participants is this: the participant who have just listened to all these 10 hours of discussion, you should be like a sponge actually. I mean, the knowledge is everywhere, and we have organized this thing which you have joined, and try to learn as much as you can. Learning about instrumentation or an instrument or a machine, how does it work for a particular characterization, that is okay, but to understand the physics and chemistry behind how the instrument is built actually, that is more important. So I'll just suggest that please try to understand how a particular instrument is working, what is the physics of phenomena behind it. And second thing is that material science is all instrumentation, all practical and all that. It would be just great if you can start kind of learning few tricks about the simulation part, and how just to complement your experimental finding, that would be probably complete your whole research and all that. And finally, the two things I would like to say is that if you want to become successful in your career, as sir was saying in the triangle of success, the first thing is the honesty, which is paramount. Everyone got to be honest, truthful to yourself. And the second part is the tenacity of the purpose. You should know what you want to do, and these two things, if you inculcate or imbibe in your whole character, whole personality, probably you will go far. With these words, I stop here, and I wish you all success in your respective career. And I hope that we'll soon, or as per our direction from Honorable Dean Sir, will keep organizing such little things for you people, so that we can keep this journey going on. Thank you so much. Thank you, Giriraj sir, again. Thank you.
Thank you, sir. Thank you very much.
Thank you, sir. Thank you, sir, for your encouragement and support for the smooth conduct of this workshop. On behalf of the organizing committee, I would like to extend my sincere thanks to Mr. Giriraj for conducting this workshop so brilliantly. This training is indeed very helpful, and the feedback received from the participants was excellent. It is also a pleasure to associate with Toshvin Analytical Private Limited to conduct this workshop, and I strongly believe the participants have enriched their knowledge in material characterization through this training. Last but not least, we would like to thank all the participants for their enthusiastic participation and making this workshop a success. So now I request Dr. Nagaraju to release the appreciation certificate to Mr. Giriraj. Over to Nagaraju, Dr. Nagaraju. I request Professor Venkatnath sir, HOD Chemistry, to propose vote of thanks.
Okay, thank you, Srilakshmi madam. Good afternoon to one and all. This is Venkatnath, Head Department of Chemistry, Geetham School of Science, Geetham deemed to be University, Bengaluru campus. I deem it my privilege to propose the vote of thanks on the occasion of 4-day National E-Workshop on Modern Analytical Techniques for Material Characterization, which is organized by our Department of Chemistry in association with Toshwin Analytical Private Limited during 9th to 12th November 2020. This event is a huge success and the organizers received laurels from the participants because of the eminent speaker, Mr. R. Girirajan.
Sorry. Mr. R. Girijan.
Product consultant, Toshwin Analytical Limited, who relentlessly delivered lectures on UV visible spectroscopy, FTIR, thermoanalytical techniques, gas chromatography on these 4 days. We are thankful to Mr. Malleshwar Rao, Mr. Mata Prasad, Mr. Amol Ramesh, Mr. Rajesh for extending their support in presenting demo of instruments to make the workshop a lively one. On this occasion, we would like to place on the record our sincere appreciation for the excellent contribution made by the speaker and other resource persons by sparing their valuable time to enlighten the participants by sharing their expertise. At the outset, I would like to express our gratitude to Sri M. Sri Bharat, President Geetham, Professor K. Ramakrishna Rao, Chancellor Geetham, for their unconditional support. I would like to express our sense of obligation to Professor K. Sivaramakrishna, Vice Chancellor Geetham, and Dr. Gunashekaran, Registrar Geetham, for giving us inspiration to conduct a series of events. So it is my duty to keep on records. With the support of the Geetham, we were able to conduct a series of programs during the last 6 months. The Department of Chemistry was able to organize a national workshop on COVID-19, a view on vaccine production, and an international e-symposium on new frontiers in chemical sciences, one faculty development program reorienting the teaching and learning process during Unlockdown 3.0, national online student activity on creative awareness on COVID, etc. We convey our sincere thanks to Professor Subramanyam Garu, Dean Science, and Professor Atul Kumar, Principal School of Science, for their encouragement. I wish to record our heartfelt thanks to Professor Sailendra Dasari, Campus in Charge, Geetham, Bengaluru, and Professor Dinesh Sheth, Director, School of Technology, for their constant support and guidance. We are extremely grateful to Mr. Vamsi Datla, Director, Admission and Administration, for being a pillar of support for our efforts. I would like to express my appreciation to Dr. Srilakshmi, the convener, and Dr. Vikram, co-convener, Dr. Nagaraju, coordinator of the program, Department of Chemistry, for successfully organizing and scaling up the event to the new heights. We are able to successfully organize the program due to the relentless efforts of CATS department, as well as faculty members and supporting staff of chemistry and other departments. I profusely thank everyone for their support. Our special thanks to print and electronic media for wide coverage of the program. We are thankful to participants for their attentive participation and enthusiasm expressed during the interaction with the expert and the technical experts. Lastly, I thank all the heads of the departments, faculty members, and staff who have witnessed this event and extended their cooperation. Thank you all once again. We look forward and extremely productive and encouraging the balanced part of the year. Thank you, sir. Thank you, madam.
Thank you so much, sir.
Thank you very much.
Yeah. Now closing moments followed by national anthem. Over to Dr. Nagaraj.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जगति तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Jai Hind. Thank you so much, sir. Thank you, Subramanian sir. Thank you, Atul sir, for joining us today. And thank you all the participants for making this workshop a grand success. And hope see you soon in future with another beautiful workshop. Thank you, sir. We will contact you
Thank you, everyone. I place on record my thanks to all the Geetham University, all the people involved in this, and also I thank all the participants. And thank you very much. And I wish everyone success. All the participants, I wish best of luck.
Thank you, Mr.
And also wish you a happy Diwali.
Oh, thank you, sir. Same to you. Happy.
Thank you, same to you.
Thank you, sir. With this, I will close the session.
Thank you.